So, Doug, do you want to do a quick intro to the afternoon, maybe just a quick summary of what's coming up? And then we'll turn it over to Boyan to do his presentation.
Yeah, I mean, I've got those, that PowerPoint that Jim cleaned up that goes through different activities. I can share the screen if you want, and that'll go.
Yeah, so we'll just get Boyan to bring down his screen for a second, and we'll just bring up yours. There we go.
Good. Yeah.
It's Chris speaking. Good? We are now live on YouTube and posted to Facebook. So
very good. So I should start
people
up.
Who are not speaking, please mute your microphones.
All right. So Dave, am I on?
Yeah, you're on. You're not full screen on your slides though.
All righty. How's that?
That's good. So you just need to scroll down then. There we go.
Very good. Yeah, so good afternoon, everyone. Thanks for joining us. We have a full slate of activities for the afternoon and, of course, into the evening. I just want to review them before we get going. So as you can see here, we've got the websites for the two groups, the Ottawa Valley Astronomy and Observers Group, and the Ottawa Centre for the Royal Astronomical Society of Canada. Thanks for joining us. A couple of things just to remind you, if you weren't, well, if you were here this morning, or if you're new, of course, to coming to the session this afternoon, if you have a question for the speaker, use the question and answer icon in Zoom. I'm your host for the first half hour, and I'll turn it over to the next one, but the host will relay your question to the speaker when it's appropriate. The host will not be monitoring the chat box during the meeting, so please do not raise your hand. I'm only going to be monitoring the Q&A box on Zoom. A reminder, if you're not already aware, that you should not click on any web links that appear in the chat or the question and answer windows. This could lead you to nefarious websites or collect personal data. So we want to strongly advise you not to go into any of those websites that might appear through any kind of link that might appear in any of those two boxes. Here's what we have for, well, this was this morning. This is for this afternoon. We will have safe solar observing for kids. Boyan will conduct that until 1:30. Then we have live sun observing. Simon will do that. I'll let Simon decide whether we have clear skies in Ottawa where he is or not. He'll have a solar image gallery if there are cloudy skies from his location. At 1:45, we have solar observing with a camera. Jim will conduct that one. And then at 2:45, we have an introduction to astronomy ages 5 to 7 that will be conducted by Dave. Jim will take over at 3:45 with live lunar observing. This is daytime lunar observing. And again, I'll leave it to him to decide whether he's got cloudy skies or not. It looks good though in Ottawa, I gotta say, from where I am in South Ottawa. 4 o'clock, we have the lunar Artemis mission that Lund will conduct. This will lead us to 4:30, where we have Simon conducting a session on what's new and news in the solar system. A general question and answer will follow that at 5 o'clock, and then a dinner break. Into the evening, Dave will conduct another introduction to astronomy, this time to ages, or aimed at ages 8 and above at 6. Boyan will go into night vision changes, every thing. It looks interesting. Eh? At 7 o'clock, 7:30, we have Portable Astro Imaging Control Room by Paul. At 8 o'clock, beginning astrophotography with a simple tracking setup that will be conducted by Andrea. And then Jim will, at 8:30, do a session on how to become, or how to be, I should say, an urban astronomer. 9 o'clock, we have live star party, weather permitting, I should say clouds permitting in Ottawa. Jim, Simon, Jim, Lance, Michael, Andrea, and Gabriel will do that. And then we have, if it is cloudy by that time, we will have a sky image gallery featuring those folks. So the schedule of events, if you want to review those, are on our website, astrodayottawaweebly.com. I just want to reiterate or remind people that there's a virtual star party being conducted by Science North. We're thrilled that Athlone McIntyre, Chief Scientist, the Space and Planetary from the Science North Center, will be presenting at 4 o'clock Ottawa time. So there's lots of stuff going on today. So we're going to go on. I'll stop sharing my screen. As I say, I'll be monitoring the Q&A box. I'll turn it over now to Boyan.
Thanks, Doug. Is that coming through okay?
You're good.
Awesome. So good morning, good afternoon, or good evening for some people. I know we have some international viewers as well. Thank you for joining us. And my presentation will be about the solar system and safe solar observing. The presentation will be more geared towards children. I'll be trying to simplify things as much as possible, but I hope some adults will enjoy it as well. And why space? So this morning we were getting some questions as we had some presentations, and I decided to actually change my slides just during the lunch break just to answer some of those questions. So why are we here today, and why are we talking about space? For a lot of us, this is our passion. Some of us work in this field, some of us studied in this field. Some of us just do it as a hobby in evenings and weekends. However, in my opinion, this picture and the next picture I'll show you is really what captures sort of the awe that we have with space and science. So this is a picture of the Earth taken from the moon by one of the Apollo missions in the 70s. And it really speaks to the fragility of the Earth and how vulnerable we all are. We're all on this tiny little dot in space, and that is sort of what gets us really excited about just the grand scale of things. So this is a famous picture from the Voyager probe. It took a picture of Earth when it was at the edge of the solar system. So this little dot here is the Earth. And there's just a fascinating quote attached to this picture from the late Carl Sagan, who said it best. So I'll just read this quote just to set the tone for, I guess, why we all believe space is awesome. So look at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you have ever heard of, every human being who ever was lived their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. So that was what Carl Sagan had to say about astronomy and the place of Earth in just the solar system to which we have access to. So that's just sets the mood, in my opinion, on just why we all believe space and astronomy is so interesting. It lets us study where we came from and hopefully where we're going to one day. So briefly, what is the solar system? In a nutshell, the solar system is a region in space where we have planets that are circling around a central point. In this scenario, it's our sun, which is a star. However, other solar systems can have multiple stars in the middle of the solar system where the planets revolve around. How many planets are there in the solar system? Some of you may know the answer to this, and I will answer that shortly. So how big is the solar system? We've all heard of the solar system. We live in the solar system, but we don't quite know how big it is in common day terms. So I wanted to simplify this as much as possible. Here is a soccer field, which we all remember perhaps before COVID and remember walking on. And we're just going to assume it's a regular soccer field, 100 meters big. Astronomers use a different unit of measurement. So you've heard of a meter or a foot or a kilometer. Astronomers came up with something else called the Astronomical Unit, which is the distance between the sun and the Earth, which is 150 million kilometers. Now, again, I'm just giving you a big number. What does that mean? Some of you have probably been on an airplane. If you were to get on an airplane and fly to the sun, if you could, and the airplane flies at about 1,000 kilometers per hour, you would take 17 years to fly to the sun. So that is how far the sun is if you were to fly on an airplane from the Earth. So here we have all the planets in order from the sun to the last planet, which is Pluto. And we have the astronomical units, and I've converted that to meters on our soccer pitch. So we have all our planets in a row, and we have something called the inner planets. So that's Mercury, Venus, Earth, and Mars. Those would actually fit all right within this little goalie box. So next time you're on a soccer field and you want to figure out how far the planets are relative to the soccer field, start at one goal and take 4 big steps if you're a bit smaller, and you will reach Mercury, Venus, Earth, and Mars all in one step. Jupiter and Saturn are the next big planets, and believe it or not, Jupiter's still within the big goal box right here. Saturn, which is actually smaller, is about half of the pitch. And then Uranus, or as some of you younger folks might like to say Uranus when you were younger on the school. Yeah, I see some smiles, that's good. Uranus is about halfway across the soccer pitch. And then we have Neptune, about 3/4 of the way. And I threw in Pluto. Poor Pluto is actually no longer a planet. This was a decision that came about within the past 10 years or so. But we always thought Pluto was a planet. However, as science evolved, scientists changed their mind because we get better information, so we can make better decisions and analyses about the world around us. And we found other planets or other bodies that were actually bigger than Pluto, so we demoted Pluto from being a planet. So the answer to the previous question is, how many planets are there? There are 8. Mercury through Neptune, and Pluto is what's called a dwarf planet. However, just keep in mind, this is a soccer field. Earth is somewhere down here by the first goal line, within the first meter or two. Pluto is 40 times that distance. This is how big the planets are to scale, and this is also a slide that helps you figure out what order they are in. Some of us aren't quite familiar with the order of the planets, so I thought this would be a good way to reiterate this point. Here's a little, it's not called an acronym, but I forgot the literary device that this is, but you can remember the little sequence of words. It's my very educated mother just served us 9 pizzas, and you have to remember that there's no more pizzas because Pluto is no longer a planet. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So since this is about solar observing, we're finally moving on to looking at the sun, what is the sun, and learning a bit about it. So what is the sun? So the sun is a giant ball of gas, and it's just an average star in our galaxy. And what I mean by that is there are many other stars in our universe that are similar to the sun. It is not very big, it is not very small. There are many stars that are bigger than it, I will show shortly. So it's just an average star. However, it's pretty important to us because we live around it. It is a big ball of hydrogen, helium, and traces of other elements, and I'll get into that later on. How big is it? It is this big. So this is the Earth to scale to the sun. So you could fit about 110 Earths across the diameter of this sun. If you remember, diameter is just the distance across a circle. And if you were to have a beach ball the size of the sun, you could fit 1.3 million Earths inside of that sun. And remember, the sun is just an average, boring, typical star. So here's just a quick video that I wanted to show. I have to show it like this. Let's see, playback speed 1.5. So here is the planets in order of their size, just to give you a sense of scale. And I think that's coming through okay. There's our Earth that we're all familiar with. The next biggest planet is Neptune, which is already significantly bigger. There is Saturn, Jupiter, and that's just our sun relative to the planets. And after that, we have these other giant stars, which are significantly bigger than our sun. So I just want to remind you just from that little picture at the beginning with Carl Sagan's quote, how big the Earth is, how important it is to us, but where that is in the cosmic scale of things. From the current slide. So what is the sun? It is actually 92% hydrogen and 7.8% helium and other trace elements. And it is so big that it's actually 99.8% of the mass of the entire solar system. So all the planets, all the asteroids, all the comets, anything else is 0.2% of everything that is in our solar system by mass. On a solar system scale, it's actually relatively far. It's 8 light minutes away. And now what do I mean by that? The speed of light has a speed, or light has a speed. And when you flip a light switch, you are all close enough in that vicinity that when you flip a light switch, the light effectively illuminates the room immediately. However, the sun is far enough away that if you actually were to make the sun disappear somehow, we don't know how, but let's just say the sun spontaneously disappears, we would have sunlight here on the Earth for another 8 minutes as all that light would slowly make its way to the Earth. And only about 8 minutes later do we actually receive the last of that sunlight, and then the lights would go out. So that gives you also a sense of just how big our solar system is. Very briefly, ignore the radiative zone and the convection zone. This is the anatomy of the sun. So we think about the sun in these 4 major layers, what I'll call the core, corona, chromosphere, and photosphere. The bottom 3, corona, chromosphere, and photosphere, are the outer edges of the onion, if you will, if we pretend the sun is an onion. And the corona, chromosphere, and photosphere is what we can see with some of our telescopes and special equipment. So what can we see on the sun? So this is colloquially known as sort of the outer edge of the sun. The sun doesn't have a surface, it is all made out of gas. However, this would be the outer shell and the closest thing to a surface that we would like to imagine. So this is called the photosphere, and it's about 500 kilometers thick, and it's the outer shell of the sun. And on this feature of the sun, you can see sunspots. So these are these dark regions on the sun that you can see all over the sun. It's quite an active day on the sun. And these are actually cooler regions on the sun. And this is due to how the sun interacts with its own magnetic field. So there's lots of magnetism happening on the sun. And Scientists aren't 100% sure how these come to be. We don't know how to predict them yet. However, we know that these are active regions on the sun that are a bit cooler than the surrounding regions. The chromosphere is what's really interesting, and that was the view that you saw this morning in Jim's telescope. So this is a 2,000 kilometer region of the sun. And this is where you get to see, in my opinion, the coolest parts of the sun, which is the chromosphere. So you have actual components of the sun that are separating right here. And this is actual physical parts of the sun that is being ejected out into space. If you've ever seen the Northern Lights, sometimes these pieces of the sun actually travel through space and they hit our Earth's magnetic field, and this is actually what creates the northern or southern lights, depending which hemisphere you're in. Very high level, what's actually going on in the sun and how do we get so much energy out of this big ball in the sky? In the middle of the sun is, remember, predominantly hydrogen, 92% hydrogen. And at the core of the sun is immense pressure and immense heat. By immense heat, I mean about 15 million degrees Celsius, and pressure, an unimaginable amount of pressure. And that gravity and heat is pushing everything together and mushing it together. And the hydrogen combines in order to create helium. So imagine having so much heat and pressure that you push two objects together and suddenly they fall together and out comes actually a new element, helium, and an immense amount of energy. A question you probably have then is, if we're converting so much hydrogen into another element, what happens when we run out of hydrogen? There's a couple phases, but the end phase would be something that's called a planetary nebula, which is where the sun sheds its outer gas layers, the photosphere, corona, and chromosphere. And that would actually get ejected out from the sun because the gravity can't hold it in anymore. And our solar system will become what's called a planetary nebula. So this is an example of another planetary nebula. You don't have to worry though, this will happen in about 8 billion years. So hopefully we can find somewhere else to live in that meantime. So how do we actually observe the sun? This is something I always start with. The question is, when should you look at the sun? And the answer is absolutely never. You should never look at the sun unless you have very special telescopes and filters that we're going to tell you about. However, even glancing at the sun with sunglasses or no eye protection will instantly cause eye damage. And unfortunately, our eyes don't know how to heal. So that damage is permanent. So do not look at the sun without any safety equipment. So why do we observe the sun? Light pollution is not a problem. The sun is now the brightest thing in the sky. So we actually just have to focus on filtering the light away from the sun, as opposed to nighttime when we're constantly trying to find something, some way to amplify the light. The really cool thing about the sun is it changes. So you can wake up in the morning and you can start looking at the sun. You can look at a prominence or a sunspot, and you come back at lunch and the features will have moved to another location on the sun. And you can actually see these celestial changes in an afternoon, which is really exciting. Relatively speaking, the sun is close, so it's easy to magnify. And it's easier to bring to crowds. And what I mean by that is, we're all here, hopefully getting you guys excited about astronomy and science. And this is an example of when we take our telescopes to schools. It's much easier to bring a solar telescope to where there are lots of people and show people the sun, as opposed to having a lot of people come out into the countryside where we can show nighttime objects. And in my opinion, this is the best part of solar observing and perhaps the most critical. So I would like you to just imagine you're out at the cottage or out in a field looking at the sun, looking at the night sky, and you're observing some galaxy that's a couple 100 million light years away. You're really enjoying it, and then a mosquito flies in your ear, because that's what we have at nighttime. So this, in my opinion, is absolutely the best part. There's no mosquitoes during the day. You can do solar observing and work on your tan at the same time. A quick introduction to the light spectrum. So we have a line here of all the types of light that we know of. So we have gamma rays, we have X-rays. You've perhaps heard of X-rays. If you've broken a bone, we take a picture with this special type of light. We have FM and AM waves, which are another type of light, which is where our radios work. And then this tiny little sliver of that spectrum is the light spectrum. So we go all the way from purple or violet, if you will, up to the red portion of the spectrum. It turns out, remember, the sun is full of hydrogen, and it turns out when hydrogen burns or does its thing, it releases light at this very specific wavelength, so somewhere between red and orange. So keep this in mind, because later when I'll be talking about the telescopes, this is the exact wavelength of light that we'll be looking at. I didn't mention earlier, but there is some calcium in the sun as well. And Jim showed that calcium view this morning. However, the same logic applies here. When calcium burns and releases light, it does it at this very specific wavelength in the deep violet spectrum. So finally, after all that, how do we actually observe the sun? So there are visual aids that you can use that you can just put over your eyes or your telescope, and this will filter out all light as if you had put on a very strong pair of sunglasses that filter out all light, filter out that nasty IR that could damage your eyes. We astronomers are sometimes known to spend more than we should on our toys. However, this is actually the cheapest way to get into astronomy, period, beyond just looking up at the sky, which is through solar sunglasses. So these solar sunglasses are about 35 cents a pair. They're made of cardboard on the outside. However, the little lenses inside are designed in such a way to cut out all the light and will let you look at the sun safely, even in broad daylight. You can do projection astronomy. So if you have a telescope or perhaps a lens of sorts, you could point that at the sun, and then you actually project an image of the sun unfiltered onto a piece of paper or cardboard at the back. And this is great if you have a big classroom or lots of people around who you want to look at the image. This is a special type of filter that is made of, I believe it's mylar. It looks opaque to us, but it is letting through tiny amounts of light. You put this on the front of most telescopes and you can view the sun safely with that filter. This is a glass filter which achieves the exact same thing. The most expensive option for white light viewing is this Herschel safety wedge. So in this little wedge that you place into the telescope, there's a special mirror that only reflects 4.6% of the light out into the eyepiece, and the rest goes into like a heat sink, if you will, at the back here. So this gets really hot here at the back, and imagine you're using a telescope, you're focusing basically all the light onto this tiny little spot, and you're counting on the wedge to bring down the amount of energy safely into this eyepiece. So what can you see with that? We have the sunspots. So I've mentioned the sunspots, the cooler regions on the sun, and you can see granulation, which is actually like the surface features of the sun that are moving in the cells that Jim mentioned earlier. So we have the black sunspots, and you can see these convection cells, which are like this texture, the skin on the sun. Very high level etalon and bandpass. I will just cover what a bandpass is. So when I say that we're looking at the sun at a certain band or at a certain wavelength, we have that wavelength of 655 nanometers, which is red. I'll just ignore the nanometer part. So this is just a representation of what the filter does. How much light comes in at this part of the spectrum? 0. How much comes in at this part of the spectrum? 0. how much comes in at this spectrum, it is all of it. And then it gets filtered down as well. So this is how we filter out just to view what the hydrogen does on the sun. And when you view what the hydrogen does on the sun, you can still see those same sunspots, but now you can see a lot more. So you have some prominences on the outside of the sun, which are actual pieces of the sun, as mentioned, that are getting ejected from the sun. And you have this prominence right here. So interestingly, remember, we're looking at, this is circular enough, we're looking at a circular object face on, but that means there's another side to it that we don't see, but we also see things that are directly facing the Earth. So that's what you can see here, is the prominences, but they are facing directly at the Earth. So this is the same thing as this up here, just facing directly at us. As mentioned previously, we have the hydrogen, which was in red, and now calcium is in the deep purple over here. What's interesting about this, and this will be fun for the younger folks, is as you get older, unfortunately, your eyes, your cornea specifically, get a yellow film on them, and that's just a function of how we age. So it turns out that someone who's between the ages of 4 and 18 years old would be able to look through a telescope and see this perfectly. However, as you get older, if you're up in the higher age ranges, you actually will look at the telescope, look through the eyepiece and see nothing, because your eyes won't be able to register this wavelength of light. So usually we have to use cameras to take these types of pictures in the calcium wavelength. And again, we see the same features, however, in a slight variation, because it is calcium. So these dark spots are sunspots, and the tiny little features are convection cells.
Well, and if you want, there's a question that's come in from Michael about sunspots, actually.
Absolutely.
Michael's asking, how deep are sunspots, or are they just blotches?
That's a good question, Mike, and I don't know the answer to that. I would imagine they're a couple dozen kilometers, but that's just a guess. Jim, Simon, any thoughts?
Yeah, they're certainly in the order of several hundred kilometers deep. What they really reflect are anomalies in the magnetic field. So that magnetic field is generated inside the sun. So the sunspot roots inside the sun, could easily be hundreds of kilometers deep. At the surface itself, there's a bit of a dish, probably in the order of, again, about 100 kilometers.
Agreed.
Thanks, Simon. That's great. It's teamwork, eh? We got a whole team of people here.
But between the dozen of us, I think we can answer almost anything. So
that's what we're here for.
And this is actually one of my last slides. The only way to observe the corona, which is the outermost region of the sun, is through a solar eclipse. And this is when the moon up here gets between the sun and the Earth directly and blocks out the sun in its entirety, with the exception of the prominences and the corona. And this is absolutely something remarkable to see. I've only seen this once in my life. However, it is definitely the most spiritual and emotional thing, amongst the most emotional things I've ever experienced, where the sun actually gets blocked out for 2 to 3 minutes. The next one is April 8th, 2024. Plan ahead. It is happening just south of Ottawa. The central line, which is where you want to be, is going through Buffalo, Watertown, and Plattsburgh. And this is something that is amazing to see for all the kids online here. Bug your parents to go show you this. It is something remarkable. And we are just over time. How to get started. I have one more slide quickly. We've been asked about the cost of some of our gear. A good nighttime telescope to get started is the price of about a smartphone, $500. A good starter solar telescope is the price of a better smartphone. And The only thing we would say is before you buy anything, come talk to any one of us in the forums or on the Facebook group, and do not purchase a telescope from Costco, Sport Check, or similar stores. There are much better options than that. We wouldn't want you to be disappointed. And that is everything I wanted to cover. Thanks.
Great advice, Boyan. Thank you. Are there any questions? I mean, there's nothing in the chat. I mean, the Q&A, there's been a number of questions, Boyan, that have come through in the chat, and we've had our resident experts, I think, have done a great job in responding to them. But
awesome.
I just want to make sure that we're covering anybody who might want to ask questions now orally before we move on to our next presenter. Great stuff. I don't want to weigh in on the costs of telescopes because my wife is within hearing distance, so she'll be upset if I talk about it too much. But you know, I've always tried to buy used equipment as much as possible. I'm sure that many people have the same kind of advice. But let's move on to our next presenter. I want to make sure, Tim, did you want to take over as host at this moment, or did you want to wait till the end of the next presenter? You got Simon coming up.
Next is JS.
Oh, sorry, next is JS, yeah. Thanks, Jim. Well, seeing that, I'll just, I'll carry on. So, JS, are you ready to go?
Yeah, we can start.
Okay.
So next
So
up,
I'm going to, can you go ahead?
We have some, well, so I guess next up is Simon. Do we have a view of the sun, or is it clouded over?
Okay, guys, are we ready to roll?
Yep, go ahead.
Okay,
Yep.
well, let me just share my, there we go. Can you see my screen?
Yep, clear.
Thanks. Okay, we've got at least 50% cloud, but more importantly, we've got a dense veil, and the veil makes it extremely difficult to focus on the sun. Jim and Boyan have already given you an idea of what one might actually see if one's looking. Jim shows you what it's looking like live this morning. And both of them mentioned that there are aspects of the sun that actually move and that can change within the course of the day. So I thought that that's what I would do. I would actually show you some movies that I've made, time-lapse movies, where you can actually see this happening. I'm assuming I have 15 minutes. That's what I saw on the schedule. Let me just show you before I go to the movies. Let me just remind you of what Jim and Boyan told us about what are called prominences. These are things that you can see on the edge of the sun. In order to see them, as Jim pointed out, you really have to overexpose the sun, because these things are actually very, very faint. And when you do that, you can actually see these prominences, and you can actually see them evolve in the space of 3 to 5 hours, as I'll show you very briefly.
Simon, can you start your presentation full screen? We're seeing the edit mode right now. We can see your slides, but if you can.
Yeah, it actually enables me to quickly jump down, because I'm only going to show you a couple of these, and then I'm kicking out of this.
Okay.
I'm not using this. That's the whole point.
Okay.
Jim showed us what the actual disk of the sun looks like. And I just remind you here, this is the kind of thing that one can see. And by the way, this was the telescope that I was using to both look at the sun and put camera on and take my time-lapse movies. Of course, never, ever, ever, ever look at this without protection. So this is the kind of thing I was seeing. These are the bubbles and textures that Jim was telling you about, the convection. You can see the sunspots, and you can see these white areas here. We're not going to worry about the technical details. But I'm going to drop out of this. And let me just stop sharing for a second here. This enables me to drop down and actually start. There we go. Get rid of that. Discard that. There we go. I'm not far away, folks. I'm just having to go to my desktop to actually start up these movies that I want to show you. There we go. And I'm going to show you, first of all, there we go, I've got my movie. All right, now I can come back to you. Oh, there, I've got to go up to there. There we go. Now I can share the screen. There's my movie and share it with you. I'm going to start the movie right there again. If I get that in, what I'll do is I'll just, there we go. What you can see here, you can see a sunspot. There's a second sun. Can you see this, by the way?
Yeah, we can see it, Simon.
Good.
Yeah,
I just
clear.
have to check. Just have to check with you. Okay, so you can see two sunspots, and you can also see these various convection cells that Jim and Boyan told us about. But you can see that the sunspot, this one here, is sitting in the middle of a spiral shape. Now, what is that spiral? That spiral is, in fact, sort of a swirling magnetic field localized right over the sunspot. The sunspot, by the way, you can see it's black in the middle. It's grayish on the outside. I'll start the movie again in a minute. It's grayish on the outside. And then you can see this spiral. Now, you notice that when the movie stopped, it got a little fuzzy, and that's because the movie is actually a series of individual images taken looking through our atmosphere at the sun. So our atmosphere was boiling, and it made the sun appear to, the sun's details appear to wobble around. When we actually run the movie, your eye-brain coordination removes that. But I want you to watch this spiral. Watch this area right there. Oh, look at that. Oh, the flare. Now watch what's going on around the, oh, what's this? Watch what happens. There's something dark here that's trying to, there it goes. There it goes. Watch it go. It comes all the way around that spiral arm. I'm going to run it again, but I want to let that run. What you're looking at here is the equivalent of about 5 hours worth of individual images taken every minute and then stacked up together to make this run. The distance from here to here, I could work out that distance on average because I know approximately what the size of the Earth would be. And then I know how long the movie took. This was something moving at 65,000 kilometers per second across the disk of the sun. Let me run it again. Watch it carefully. Watch for the flare here. There it goes. And it actually jumped up to here. And then it actually migrated along here, but it's difficult to see. But watch this dark thing. It's dark because it's cool. So it's something, it's part of the plasma on the sun that's risen up from the sun. It's getting darker and darker and cooler, but it's running around a spiral. So if you like what it is, it's like a helter-skelter, except that you're going up as you go. It's like a spiral staircase. And that is the plasma cooling and running up this spiral staircase of the magnetic field. And I am going to run it one more time because this is actually very cool to see. And it's only once you get your eye in on this, you can really see what's going on. Watch it again. There goes the flare. And watch over here. And there, plasma is coming up from the sun on a spiral pathway. And it's getting cooler and darker. And more of it is cooling, and so you're getting more, it's getting more and more voluminous. And eventually, it probably will rise to the top, and maybe it'll even leave the sun, who knows? This is pretty spectacular stuff. We couldn't possibly show you this during a live Zoom today. I had to build this over a period of 5 to 6 hours. Now, I'm going to stop the share for a second so that I can get back onto my desktop and get to the next movie. And I've still got to get rid of this one. I'm going to do it this way instead. I've got too much going on. Now, I mentioned these solar prominences, which occur on the edge of the sun. I have to share here. There we go. And I share this. We're obviously looking at some prominences. The Earth would be about that big or maybe that big. And this is a movie of a prominence which is going to start doing something just here. Just watch it. Oh my goodness. There's a prominence going right up into the above the sun. And then did you see what it did? It fell back. I'm going to run it again when it gets to the end. But it fell back. Oh, and there's something there started to try and grow up, but failed. This falling back of this prominence of solar hydrogen plasma is called coronal rain. Corona because we're looking here at the sun's chromosphere that Boyan explained to us, which is really the atmosphere to the photosphere, which would be below it, but we can't see it because it's overexposed. And then up in here, this is where you see all those coronal filaments that inspired Boyan at the end of his talk. And so this is called coronal rain because it goes up into the corona and then rains back down onto the sun. Let's run this again and watch this. So again, these are small, rather static-looking prominences. This one here has got something rather nice going on. So this one is actively evolving very slowly. And then something's going to happen here. An arch is going to, and there it starts. There it is. This whole arch growing up and then falling down took about 25 minutes in real time. And the event was over and done with in about a half an hour. So what I'm going to do, I'm going to run it again, and I'm going to stop it when it gets to the main arch. I'm keeping my eye on time. Let's just run this. I'm going to hurry it along a bit. And a little bit more. There we go. So again, you can see the sun is overexposed here. We're in the chromosphere. There we go. I want it to grow and grow. I'm going to stop it there. There we go. So you can see that this is a huge archway which is trying to form. It probably comes down here, but this is bright because it's hot, and it's probably too cool here to be seen. Remember, this is about the size of the Earth. So this is a really huge arch. And what happens is that the plasma is actually climbing up the curved magnetic field. It gets as high as it can go. And because it's coming away from the sun and because it's expanding, it's getting cooler. And as it gets cooler, it gets denser, which means it gets heavier. And when it's gone as far as it can go, what does it do? It falls back. This is the coronal rain. I've never seen this before. This is my imaging, by the way. This was from my backyard. So what I wanted to show you was that not only can you see many things on the sun, you can see the sun itself, of course, through good protecting shades. They've not your common or garden sunglasses, by the way. These have to be very, very special lenses before you can look at the sun safely. You can see the photosphere through a simple Mylar filter, or these more expensive hydrogen filters. And in all three cases, you can see different levels of the sun and different aspects. But when you do this time-lapse movie approach, you can actually see the movement you can see it in real time. I sat by the telescope and camera for 5 to 6 hours to get this, but then you can run it together so people can see it all in about a minute. And I think that brings us to 1:45, which I think puts us well and truly on time.
Yep.
So what I'm going to do, I'll stop sharing there and go for questions.
You got two, Simon, that are really good ones. Jason asks, does the flare go back to the sun due to gravity?
Oh, yes, indeed. That is what is happening. It climbs because it's hot plasma going up a magnetic field. When it gets to the top of the curved magnetic field, it's cooled down. And so it's become heavier, and the gravity is what actually pulls it back. Now, it doesn't just pull it straight down like rain, because the magnetic field is still there, and it's still a plasma. So it actually comes back down the path that it went up.
Wow, that's cool. Jocelyn asks, what material or element is the coronal rain made of?
Hydrogen. It's hydrogen, and in fact, it's not just hydrogen atoms. It's hydrogen atoms that have been pulled apart. Hydrogen is the simplest element. It's made of a proton, which is a positive charge, and an electron, which is a negative charge. You put the two together, the charges cancel out, and so you then have a hydrogen atom. But a hydrogen atom doesn't care about magnetic fields. But if you rip the electron off, because the sun is so hot, it rips the electron off, and now you've actually got the electron and the proton. They're both charged electrically, and so they can both play with the magnetic field and follow the magnetic field along. But it's basically two pieces of the hydrogen atom.
And one more question from Sicily, or I hope I pronounced that right. I may have missed it, but what causes the coronal rain? Under what conditions? What makes them arch?
Now the arches, that's what the magnetic field will do anyway, because at the bottom of one side of the arch, you've got one magnetic charge, in other words, positive or negative. And at the other side of the arch, the other foot of the arch, you've got the opposite charge. And so that makes electrons try to flow, and any charged particles, try to flow along that looped magnetic field. That's the principle of electricity coming out of your wall socket, by the way. It's the same thing.
Oh.
It's following along a potential from negative to positive, or the other way around. I'm not a physicist, so I never remember which way the electrons go. I assume they're headed towards. I assume they're headed towards a positive charge, but that's what that's all about. The sun has a far more complicated magnetic field than the Earth does. We have one North Pole and one South Pole. But the sun not only has a main North Pole and a main South Pole, but just underneath the surface, and when I say just underneath, I mean 1,000 kilometers, there are many, many, many local North Poles and South Poles. And it's when these erupt at the surface that you get these loops. And if you get a really big loop, then at either end of the loop, where the loop comes down to the quote unquote surface of the sun, which is not a surface, that's where you'll get your sunspots.
Wow, that's cool. That's the time we have for questions to Simon, but if you have further questions, please type them up into the chat and I'll see that he gets them. And
I'm monitoring chat, by the way.
Oh, you are? Okay, great. Then he's right on the money, doing it right away. So yeah, please take a look at the Q&A and ask the questions that you would like. Before I pass this on to Jim, Sophia, and our new host, Jean-Sebastian, I just want to remind people about the warnings that we have in the chat and the Q&A. And just remind people again that you should be cognizant that any kind of link within the chat is may be nefarious. I'm sure some people have put some in that are not, but you should be more cognizant about how dangerous some of these things might be. So I'll pass this on now to Jim, who is ready with solar astronomy, and the new host, Jean-Sebastian.
Okay, well, thank you. Thank you very much. So we ready to start? Do you hear me pretty well?
Yeah, we hear you, Jim. Go ahead.
Excellent. Okay. Well, welcome to this presentation on solar astronomy. I know we've learned an awful lot about the sun today, and I'm hoping to complement some of the information that you've already heard. I'll be going for about 45 minutes, and I'll leave some questions, some time at the end for questions and comments. I'm going to begin by briefly showing you the instruments I use, the scope and its features, the mount, and a simple alignment procedure, which is done on the handpad of my computerized mount. We'll look at the camera and its connection to the laptop where the image is seen. The reason I'm doing this is to familiarize those who are new to the hobby, or those who may be interested in seeing how this is done using a solar scope and camera. This will be followed by a presentation on the sun a brief outline of some basic solar facts and the kind of solar activity that we can observe, basically an extension to Boyan's excellent presentation on the sun that we heard a little while ago, and also some comments that Simon has made previously. During the presentation, we're going to view solar images and videos that I took with the images, with the instruments that you've seen. After that, I'll speak about how the solar wind interacts with our atmosphere to produce the Aurora Borealis. And I will show some really great photos of the aurora taken by our tour group when my wife and I visited Alaska a few years ago. And lastly, and we will have time for this, we'll visit the Solar Dynamics Observatory website, which showcases a semi-autonomous spacecraft launched by NASA in February of 2010 to allow continuous observation of the sun. And that really, in my opinion, is really very impressive. I hope you enjoy it. Just a quick reminder before we begin, never look at, and you've heard this, but it bears repeating, never look at the sun directly. It's harmful for your eyes. Use safety glasses approved for solar use, or a telescope prepared safely for solar observing. This is the Lund 60mm solar refractor. This scope is just for the sun. It measures 40 centimeters long as it appears on this slide. I purchased the scope with a feather touch focuser that I'm circling right here, which enables smooth, fine focus. And that was an upgrade, but definitely worth it because good, fine focusing reveals more detail on the solar surface. I also bought another upgrade called a Soul Searcher, and that's this instrument right here that I'm circling, and it's a great way to locate the sun in your eyepiece without looking directly at the sun, and I'll demonstrate how that works in a few minutes. And this is the mount I use. It's the Celestron Evolution mount without the scope attached. So what you're seeing is just the mount, and Celestron is a popular brand. The mount is powered by a rechargeable internal lithium battery that will last approximately 6 hours in the field. You can also plug it into an AC outlet or use a portable 12-volt battery. And here is the hand control. This mount is computerized. After a simple alignment procedure that I will describe to you, the mount will know its position in the sky and slew to thousands of celestial objects in the sky upon command, and automatically track the object that you're looking at. Since the Earth is moving relative to the sun, planets, and stars in the sky, an object that you see in the eyepiece will drift out of view in time if you're not tracking it. However, if your tracking is good, it will stay in the field of view. Astronomy has advanced in its use of technology over the years. Now, this particular mount that you're looking at is an alt-az mount. So it doesn't track as well as an equatorial mount, but it still does a decent job. Now the scope is easily attached to the mount by clamping its dovetail. I've also inserted an eyepiece, as you could see here. And by the way, what you're looking at is my southern balcony. I do all my observing, all my imaging lately, especially since COVID, on either my north balcony or my south balcony. And even though some trees are encroaching on my south balcony, I can still see some interesting sights. So let's take a look at the Soul Searcher attachment. And once this is set up, you basically move the scope in the direction of the sun. You don't necessarily have to look at it, but do you see the projection of the sun here? Well, what I need to do is to move the scope manually so that the sun is in the center of the bullseye, like so. And once I've done that, I can be fairly sure that the sun will appear in the eyepiece, but I check anyway. Once I've done that, I move the scope straight down to a level or home position, and this is necessary to begin an alignment. And here is the hand control. Once the mount is turned on, I need to align it so that it knows the kind of information to find objects from my location and accurately track them in the eyepiece. So I enter into the hand control 4 pieces of information. The first piece of information that I enter into the hand control is my latitude and longitude location, which I can get conveniently from my phone, or I could look it up on the net. Needless to say that this bit of information is extremely important, because once we know our latitude and longitude, we know our location on Earth, and so does the mount. Latitude, as you can see by this illustration on the left, measures north or south of the equator in degrees, and longitude measures east or west of the prime meridian, located in Greenwich, England. By the way, once I enter my latitude and longitude, I don't need to enter it again unless I travel a pretty far distance away from my last location. The second bit of information that I enter into the hand control is the date and time of day. The third piece of information is the tracking rate. I can choose between solar, lunar, or sidereal. I choose the tracking rate solar so that I'm tracking the sun, as opposed to lunar to track the moon, or sidereal to track the stars and to track the stars at night. Lastly, I choose the sun as my alignment object on the hand control. And then I use the hand control to move the scope up from the home position to the point where the sun image shows up on the bullseye of the soul searcher that you saw just a few minutes ago. And then I press enter on the hand control. This tells the mount that it is pointed to the sun. When the hand control reads alignment successful, I can start observing using the eyepiece for visual observing, or the camera to capture the image on the computer. So what I've done is I've taken the eyepiece out and I put the camera in. And the camera that I'm using is a Mallancam Skyraider 10C Tech. That's the model number. And it's one of many fine cameras made by Roch Milan, past counselor of the RASC. He has a shop located in Ottawa, and I can use this camera to take still or video captures of the sun, planets, the moon, and thousands of deep sky objects. So what I do is I attach a USB wire to the camera, and I attach the other end of the wire to my USB 3 port on the laptop computer, which is in the kitchen, not far away from my balcony at all. I can then operate camera controls from the computer using the software that came with the camera. There are options for live stacking, adjusting the histogram, and many other settings to enhance image quality and signal to noise ratio. I've loaded a solar image here just to show you the display interface. It's a learning curve, but a lot of fun. Initially, you want to control the gain and exposure time in milliseconds to get the sun's disk as sharp as possible. Then, focusing the image at the scope end to bring out the fine detail on the solar surface. Good focusing is crucial. In my case, I've rigged up a servo motor transmitter receiver attachment to the focuser so that I can focus the image while I'm looking at the computer screen. Now, there are other settings at play here as well that I haven't mentioned in getting a detailed image. And I still have a lot to learn, but I'm enjoying the ride. What I enjoy most about solar observing is the fact that the sun is so dynamic and changing, always some surprise awaiting. So now let's speak a little bit about the sun, and I'm hoping to just expand a little bit on what you've previously heard. So as you've heard, the sun is composed mostly of hydrogen gas, some helium and dust, which started condensing due to gravity approximately 4.5 billion years ago. And as this occurred over time, the temperature and pressure at the core of the sun increased as well. The core extends to roughly 1/4 of the way from the sun's center. At the core, as Boyan has previously mentioned, temperatures can reach 15 million degrees Celsius. Also, the pressure is reportedly 260 billion times greater than the atmospheric pressure on Earth. And in this extreme environment of heat and pressure, hydrogen and helium atoms are ionized, meaning that their electrons are stripped away. And these highly charged electron particles are called plasma, a term that I will refer to later on. But more importantly, at the core, under this extreme heat and pressure, nuclear reactions occur when hydrogen atoms fuse to make helium atoms. This fusion reaction produces energy, about 4 to 5 million tons of energy per second. And this energy is the light and heat that we experience here on Earth, approximately 150 million kilometers away. So this nuclear fusion reaction at the sun's core is a good example of how mass is converted to energy, as Einstein stated in his famous equation, E equals mc squared. So what we have here is a fusion reaction at the core, which is producing energy pressuring outward, while gravity is pulling matter inward. And this delicate balance maintains the sun's integrity as it lives through what we call its main sequence. But eventually, the star runs out of hydrogen to fuse into helium, sheds its mass, and expands to form a red giant, which gradually forms into what is called a planetary nebula. This is an image of a planetary nebula that I took with the camera, Messier 27, the Dumbbell Nebula. The star gradually sheds its outer layers, leaving behind a small, hot, dense stellar core remnant called a white dwarf, which excites the atoms in the expanding gas around it, creating the colors that you see that are picked up by the camera. The star, once a source of life-giving energy, in death seeds the interstellar medium with elements leading to a possible rebirth of new stars, not to mention the beauty that we behold as astronomers in the meantime. So back to the sun. Above the core, as you've heard, is the radiative zone, roughly 70% of the sun's radius. Energy produced through nuclear fusion at the core moves steadily outward as electromagnetic radiation, taking about 100 to 200,000 years to radiate outward. I seem to have different figures on how long it takes for this to happen. So what I have is a range from 100 to 200,000 years. Someone might have a comment to make about that. Above the radiative zone, as you can see, is the convection zone. And this layer of the sun is above the radiative zone, and it is the outermost layer of the sun's interior. Energy moves towards the sun's surface through columns of convection currents of gas. This happens, as you've heard previously, this happens when the heated gas from the radiative zone rises until it cools enough to sink back down, creating a pattern of heated material rising and cooling in the convection zone cells. And this turbulent motion causes granulation that is visible on the sun's surface. So here we've come to the visible surface of the sun, or the photosphere. And this image was taken July of last year off my balcony using the equipment that you've seen. So can you see the granulation on the surface?
Yeah, Jim.
Caused by the convection cells below. This photosphere is the visible surface of the sun, where we can see the effects of rising heat and plasma energy and its strong magnetic field lines interacting with each other in an ever-changing fashion. Solar activity occurs in cycles with the average duration of about 11 years from what I've read. Solar maximum and solar minimum refer to periods of maximum and minimum sunspot counts and solar activity in general. We're coming out of a minimum now from 2019. Another familiar sight here. Sunspots are cooler, darker areas of intense magnetic activity on the surface of the sun, blocking out the outward flow of hot gases. Sunspots may accompany a variety of other solar activity like coronal loops, flares, coronal mass ejections, and prominences. Okay. This is a shot I took with the camera last month. It shows several sunspots, as you can see here. And bright regions of higher temperatures that are typically found near sunspots called plages. As I said earlier, in the extreme environment of heat and pressure at the core, hydrogen atoms are ionized, meaning that their electrons, hydrogen, helium atoms too, more hydrogen though. So their electrons are stripped away, and these highly charged electron particles are called plasma. And as they move, they create a magnetic field. Also, the sun's rotation and the movement of convection sets up streams of this plasma within the sun to create a magnetic field, or as Simon mentioned, there's really multiple magnetic fields occurring in the sun itself. Have you seen the effects? Have you seen the effects that a bar magnet has on the iron shavings dropped around it? Well, that's just an analogy, but strong magnetic fields on the sun's surface affects how the charged particles of plasma move. These vast magnetic fields have much energy stored up in them, and these magnetic field lines can get tangled up and can short circuit, creating an explosion or a solar flare, sending material into space. This is a wide-angle view I took of the disk of the sun, and it's exposed to show activity along the periphery. Let's see if we could zoom in and all right, let's see, we'll do this. Okay, so here's an example of some solar activity that's occurring right here. And correct me if I'm wrong, but this reminds me of a coronal loop, which is composed of huge loops of hot glowing plasma that follow magnetic field forces beginning and ending on the sun's visible surface. Now, the day I took this shot, there wasn't that much activity going on, or at least from my angle. Let's see. There's some prominences over here, and there's another one over there. Okay, so you can see that the periphery, there is some spotty solar activity that's occurring that we can see with our camera and computer. So we're at video 20. Okay. So what I'm going to show you now are 3 videos of prominences, although the Simon's prominence blew me away. Simon, that was a phenomenal capture. That was lovely. I'd love to see it again. So these are 3 videos of prominences. These are raw images, no post-processing. They're kind of grainy and noisy, and I'm, and as I get better at this with practice and experience, we'll have some better images. But this is what I saw one day sitting in my kitchen, looking at the solar surface here. So here's a prominence. Prominence is a tumultuous loop of plasma or arching cloud of plasma stretching into the corona of the solar surface, from the solar surface rather. Its movement follows the twisted and constantly changing magnetic fields which envelop the sun. Let's see where we are with this. Nope. Let's see where we are with this. I think we're finished with that one. Okay, here's another one. And I'm going to read to you from NASA's website regarding solar prominence, a large bright feature extending outward from the sun's surface. Prominences are anchored to the sun's surface in the photosphere and extend outward into the sun's hot outer atmosphere called the corona. A prominence forms over timescales of about a day. So even though you're not seeing much activity, that activity that you've just seen occurred within a few minutes. I'm going to show you another one here, which kind of reminds me again of the coronal loop, because you see you have 2 sides here anchored on the surface, 2 polarity points, and this looks like a coronal loop to me. Okay, fabulous. All right. And this is a capture I took with the camera that that details some plasma activity here. Okay. The chromosphere, as you've heard, is the second layer of the sun's atmosphere, and it's roughly 3,000 to 5,000 kilometers above the photosphere. The corona is the outermost part of the sun's atmosphere. It's millions of degrees hot, but thin. It's visible in this photo, and Boyan also pointed this out. It's visible in this photo that I got off the net of a total solar eclipse, where the moon is located between the Earth and the sun and covers the disk completely. In this case, almost completely, but well, it's good. This is an amazing event, by the way. I can't wait for 2024. The sun's magnetic field affect charged particles in the corona to form beautiful features. And this includes streamers, loops, and plumes. And you will see some really magnificent ones from the Solar Dynamics Observatory website in a few minutes. This is another image I took with the camera showing parts of the sun's corona.
Jim, just a question here in the Q&A. Corinne asks, how big are the plasma bursts that you're showing, the prominences?
How big are the prominences?
Right.
My goodness, I would say several Earths at least. If somebody else wants to weigh in on that, I would say several Earths for sure.
A good trick is it takes 110 Earths to cover the diameter of the sun. So from there, you could sort of scale that.
Okay, excellent. Thank you.
Okay.
Now, the solar wind is created by the outward expansion of plasma from the sun's corona. The Aurora Borealis originates from this solar activity as the solar wind containing charged particles travel towards the Earth at approximately 800 kilometers a second and strike atoms in our atmosphere, which excite the electrons in the atoms to higher energy states. And when those electrons return to their original lower energy state, that difference in energy is released as light or photons, whose travel is influenced by the lines of force in the Earth's magnetic field. So being close to the Earth's poles, like the Arctic Circle, is a good place to be to observe the Northern Lights or Aurora Borealis, or the South Pole, the Aurora Australis. We were in Alaska a few years ago to see the aurora, and here are some photos. We were fortunate as predictions were good for aurora activity in our location, which is based on the solar wind data and the Earth's magnetic field. We were picked up in a vehicle that holds about 20 people each, and the vehicle ran like a tank mechanically, gripping the road with revolving plates that gave traction in the snow necessary to climb up the mountain. It was very quiet and serene. Okay. And believe it or not, we were in Alaska, this must have been about 6 or 7 years ago. It was actually colder in Ottawa than it was in Fairbanks, Alaska. It was an awesome experience. I felt like we were witnessing a symphony of movement and color. It was also very unpredictable. Curtains of color varied in speed and in intensity. In some instances, the sky was enveloped with arches of wavy color extending from one horizon to the next. A true spectacle. The color of the aurora depends on the wavelength of light emitted, and this is determined by the type of gas in the atmosphere. Well, in our case, our atmosphere consists mainly of nitrogen and oxygen, which emit the characteristic colors in their respective line spectra. According to what I've read, oxygen is responsible for two main colors of green and red. Nitrogen causes blue and deep red hues. However,
Jim,
yes, go ahead.
Yeah, we have a question here. So when you saw the aurora, could you hear anything? Is there any
Yes,
sound?
I did. There were times when I heard little crackles.
Wow.
Yeah, I know, and I wasn't, and that's what they said. They said you might hear that. But what really amazed us was the movement, like the whole, like the sky was basically covered in color, and we were very fortunate because this doesn't always happen that way. But the predictions were extremely well, and we were really happy.
And was it like a fast movement or slow or?
Most of it was slow. It was
Okay.
very gradual. Like you would see a curtain of color emanating from the horizon, and it would just slowly build up, and sometimes it would, would creep back down, and then at the other end of the sky, you would see an arch forming that might, travel a little bit faster. But before you know it, you have what I would consider a symphony. It was just amazing. I mean, we were just there in awe and awe. And I could see how, native folks from the millennia, many in history, may have really had amazing spiritual experiences and written about the aurora. So it was really an experience I'll never forget. But as I was saying, the color depends on the altitude, and that is so because there are different colors of the aurora at different altitudes because the composition of the atmosphere changes and its density decreases as you go higher. And there we were right there. I also read that the colors depend on the relative proportions of oxygen and nitrogen at the level of excitation where the charged particles from the sun strike the atoms in our atmosphere. And this is all because of the sun, folks. That's one of my favorites. I think I posted that on my Facebook page. I loved it so much. Very clear. Okay, so now we are at the Solar Dynamics Observatory website. I've taken some captures from there. And just to reiterate, NASA's mission is continuous observation of the sun using a spacecraft camera, which is quite amazing. And it collects data, it shares resources. And if you go to the Solar Dynamics Observatory website, and the link is right here, you can actually find out what the kind of activities going on at different wavelengths. And I've chose this wavelength here because this is typically what I might be looking at through my solar scope. So if I'm seeing a very active sun, I'll pretty much be looking at that as well, as long as the sky is clear and I have good seeing, because just a little bit of thin cloud can really affect what you see. And what I also like about this website is that it contains a gallery of photos and videos that are taken by the spacecraft camera. And I'm about to show you couple of those videos right now. So the movement of plasma following magnetic field lines, that's what you're looking at. The image was taken in a wavelength of extreme ultraviolet light over a one-day period, as you see the rotation of the sun. And what's interesting about this video is that the flow of plasma gets to a point and then seems to largely change its direction and head back down where it came from. Kind of reminds me of what Simon said to us before, that you know, this plasma is affected by very strong magnetic fields in the sun area, and these prominences, as I've mentioned, I may have mentioned this, are cooler clouds of charged particles that are tenuously tethered, as NASA puts it, to the sun's magnetic forces. And I believe I have another one to show you here. This one is one of my favorites. Okay. And I'm just going to read directly from their website. This is called the Solar Golden Arc. The magnetic field lines between a pair of active regions formed a beautiful set of swaying arches rising up and above them. And this capture was taken in April of 2017, and I have it on repeat so you can see it over and over again. The connection between the opposing poles of polarity is visible in exquisite detail in this, in this wavelength of extreme ultraviolet light. So what we're really seeing here are charged particles spinning along the magnetic field lines, and other field lines are traced as they reach out in other directions as well. Now, this video covers almost 2 days of activity. We'll let it go one more time and then. Okay, fabulous. Well, this concludes my presentation, and if there are any comments or questions, I know I've left about 15 minutes for comments or questions or whatever. Any questions about my gear or experiences in Alaska? So now's the time to ask if there are any questions. And I appreciate the help that I might be getting in answering some of these questions.
Yeah, that's been a very interesting talk. I guess there's one question today. I guess we showed different pictures of the sun and different wavelengths. I guess the question is why are they different colors?
Why are there different colors?
Yeah, the different pictures, I guess.
Well, again, the colors have to do with the type of atoms that are excited by the solar wind, right? So you have certain elements that have certain line spectra, which are seen when that excited atom returns to its original energy state. How is that, Simon? Did that make any sense? Okay.
Sorry, Jim, I was offline there for a moment.
No, that's okay. The question
Were
was,
people asking about the colors of the pictures of the sun or of the aurora?
was it the aurora that you were asking?
No, I think, well, I think it's more the, I guess you showed that, you know, an X-ray and UV and all that, and they're different colors. Is that?
Oh, that's
yeah, right.
that's a matter of the filters.
Okay.
Yes, right.
The filters being used.
Right. Actually, I just had a quick question myself on some of the pictures you showed earlier, where you show your prominence. The sun is just like a white disk, while sometimes I guess you have some other gear which shows the granules. What's the difference in the?
Well, the difference has to do with the exposure. I have to overexpose the disk of the sun to see the detail that's occurring on the periphery. So it's really exposure. I just increase the exposure in order to do that, because the sun is so big, you know, and what you see on the surface in the middle is going to be in focus. But if you know, if you're looking at something closer to the periphery, you really have to either refocus or you have to change your exposure.
The prominences are, I guess, are much dimmer than the.
Well, I think it has to do with exposure. Now, what I'd like to be able to do, I haven't figured out how to do that, is to be able to take the sun's surface and the periphery prominences at the same time. And that
It can be done.
That would be a cool thing to do if I can do it.
It can be done, but you need some very expensive equipment.
Okay.
If I can chime in here for a second.
Oh, please do.
Okay. Since the prominences are a lot fainter, if you've got the disk nicely exposed, you won't see very much of prominences. So you have a bit of a balancing act. What I've seen people do, and what I've tried to do with limited success, is to take two images at two different exposure levels and superimpose them, so you can make a simulated, which, you know, whether you call that baking or not. If you've actually done them at roughly the same time, then it works out reasonably well. But remember that that's for a pretty picture.
Yeah, well, I love pretty pictures, and I'd love to learn how to do that. Because I've done
it, but it looks horrible. I've seen it done and looked good.
But what that would capture, though, is the sun in its entirety, and that's
yes.
Yeah, I'm really going to figure. Hopefully, well, you say that maybe I do need expensive equipment, but that would be cool. I tried to do it artistically, and it looked bad.
Well, it takes
really
a while.
Bad.
No, it was artistic, Jim. It was artistic.
Yeah, I know. But if you're going to show it to somebody and you're using, I'd like to show things that look as real as possible. But this wasn't. You wouldn't want to see this one.
Well, you stroke your beard and say, well, artistic talent, and never mind.
Yeah.
Seriously, though, I mean, it's one of those where you've really got to pick one or the other. The dynamic range is just too big to get it in a nice, simple image. You'll have to pick one or the other,
right?
And either blow out the center or dump the prominences into dark obscurity. There's not much of a way around it. Sometimes you get super bright prominences, and it just works out beautifully. Yeah,
exactly.
You have to sacrifice chickens for that. So.
Yeah, well, I would love to be able to collect these videos, but let me tell you, these videos take a lot of disk space.
Oh, Lord, yes.
We're talking about megabytes and megabytes.
Megabytes? How did you get away with so small?
Well, I'll tell you. This last one from NASA, I think it must have been about 57 megabytes. And now mine were 2, 3, 4 megabytes, but it was only, maybe, 20 seconds or something like that.
I've maxed out my AVIs at 2 gig.
Oh, really?
Yeah. I mean, if you just run it at full frame rate for half an hour, and boom, there's 2 gigabytes before you move.
I see.
And that's the limit for AVI files.
Yeah, okay.
So, I mean, you can gobble up enormous amounts of disk.
Yeah, you definitely can.
And then you just throw away, you go into it and post-process it and throw away most of the frames.
Okay.
So there's just no way around it. You're going to gobble disk space like crazy.
Now, if I take a video of the sun, can I actually, what I'm using is it runs videos, but are you saying that I can actually take a look at each frame?
Yeah, sure. I use Registax myself.
Oh, okay. I see. Yeah.
Yep.
All right. Yeah, I have Registax too. You know, I never thought of doing that with the sun or with.
Yeah, I've done it quite often, and it's trickier than it is for, say, planets. I find, at least for me, it is. You can produce some absolute crap, but you know, if you save your originals, then you just go back and create different crap. So,
yeah, Tim, that's how you get your gigabytes of video, right? At high frame rate, you fill that up quickly.
That's right. Yeah. And then you can. Part of it is I've done most of it with the wavelet feature, but I have never found a good way to explain what the settings are. There's a lot of artistry to it that I don't get. I've never had anyone give me a coherent explanation of how to set them properly.
Okay. So we do have a few minutes left before before Dave comes on, and perhaps I can just show some slides in terms of what's going to be next. Would that be okay, Dave?
Absolutely. Yep.
Yeah. So, for example, let's see. Oh, gee. All right. Wait a minute. Oh, I should have done that before. Ooh, I'd have to share my screen again. Here we go. And all right. So just for those of you who are just tuning in, we're going to be listening to Dave Chisholm in a few minutes, speaking about an introduction to astronomy geared to young children, ages 5 to 7. Then we're going to move on and listen to Jim Thompson. And Jim may or may not have depending on the sky. Jim, I don't know if you're around, but if you're able to show us a live lunar observing, that would be great. If not, I know you have some really excellent lunar images to show us. And as you've heard, we're going to have a guest speaker, Olaf McIntyre, speaking about the moon. And that's going to be a real treat. Afterward, what's new in news in the solar system with Simon Hamner. And then for those of you who have asked questions and haven't gotten an answer yet, well, what we're going to do is look at the question and answer stream and try to answer as many of those questions as possible. And this will also be an opportunity to, right on the fly, ask some questions and get some answers. And following that, we have a dinner break. And I'm going to, let's see if I can go. Yeah, I'm going to stop right there. And just remind everyone that Dave is going to be up in a few minutes. If you have any questions for him, put them on the Q&A. And Dave has requested that I share the information because he's going to be asking some questions to some folks, and I'm going to be relaying those answers to him. So the host won't be monitoring the chat box, so do not raise your hand, but use the question and answer option to ask questions. All right, now I'm going to let's see what I can do here. I'm going to stop my share, and I'm going to highlight Dave.
Okay.
Okay, so give me a minute here.
I can do it from my end, not a problem. There we go.
Add spotlight. Okay.
Yeah, there we go.
Okay, thank you, Dave.
No
Here I
problem.
am.
So let me just share my screen here.
All right.
There, everybody see that okay?
Yeah, very well.
Good stuff. Okay, folks, just before we get started, there are handouts that go with this presentation. This presentation is one that I've done to Beaver Scouts and to Sparks many times. And normally I do it in person. For the last year or so, I've been doing it doing it virtually. It is an interactive session, so I'm going to be asking some questions. And so if you want to answer the questions, just type them in the Q&A box. Just pretend like they're a question when I ask you for an answer. Is that confusing enough? But just type your answer in there and we'll be good to go. If you go to our website, astrodayOttawa.weebly.com, and then across the top there's a virtual IAD 2021. Click on that and scroll to the bottom of that page, and you're going to have all the handouts that I'm going to be referring to in this talk. And in one handout in particular that I'd be keen for you to take a look at is that I'm going to have a star finder. And just a second, I can't see myself here. Just a minute. Oops. No, I don't see myself as the presenter, but everybody see the star finder there?
Yep.
Okay, good stuff. I'm going to bring myself up on the on the YouTube so I can see what I'm looking like. It's a little hard to do this. There we go. Okay, so one of the things we have here is a star finder. You can download this as a PDF file, print it on 2 pages, and put it together. I'll talk a little bit about that, but if you want to get prepared by doing that, and it works best in if you put it on cardstock. Okay, so an introduction to astronomy, ages 5 to 7. Just going to move some things around here. There we go. Okay, well, first of all, what is this a picture of? Anybody knows the answer to this? They can type it in the Q&A box. Anybody know what this is? Okay, so this is a monster.
IM8.
Yeah, this is a monster. Okay, and that is, but this is a friendly monster. You know what? This is a teenage monster. And I don't know if you know much about teenagers. My son is a teenager, and he's not fast for getting up in the mornings. So this is a typical teenage monster. He doesn't get moving fast until about noon. Well, he said, what's monster got to do with astronomy? Well, I've got another little saying here, a little story about the monster. And this is how I remember the planets and the asteroids. So my very eager monster always jumps slowly until noon. Okay. Now, when we do this presentation, and whenever we come to jumps, we got to jump. So you got to move up and down like that. Okay, so that's part of the exercise for this. And then what I do is the first letter of every one of these words maps to the planets and the asteroids. Okay, so this is the order of things in our solar system. Now, the sun is, of course, at the very center. So mine is Mercury, Vari is Venus, and so on. And I always like to include the asteroid belt. I'll be talking a little bit about that. The asteroid belt is the planet wannabe. It wanted to be a planet, but the big bully Jupiter pulled it apart. So let's go through the planets then. So at the very center of, there's our solar system right there. So the very center of our solar system, we've got the sun, then we've got Mercury, Venus, Earth, Mars. Then we have this collection of rocks. These guys wanted to become a planet. Every time they wanted to become a planet, Jupiter pulled them apart. We've got Jupiter, Saturn, Uranus, and Neptune. Okay, so that is our solar system. So I'm going to take you through each of the different pieces of our solar system here. Some of this is a little bit repetitive from some of the other presentations, but let's take a look at this. Well, first of all, the sun. Never, ever, ever look directly at the sun, even for an instant. One of the things I like to say is that if I pinch myself or close my hand in a door or I get stung by a bee, it hurts. I've got pain sensors all over my body. But our eyes don't have any pain sensors. There's nothing to tell our eyes that, hey, I'm being hurt. And when you look at the sun, your eyes are being hurt. The sun is burning the back of your eyes. It's doing permanent damage to your eyes. So we have to be very, very careful looking directly at the sun, because we can burn our eyes. If you look at the sun for more than 2 seconds, you're going to have some permanent eye damage. Longer than that, you could be blind. Very, very important not to look directly at the sun. But as astronomers, we love to look at the sun. It's one of the cool things to look at, but we look at it safely. Well, there's some safe ways to look at the sun. Now, up in the upper right-hand corner here, this looks like a pair of sunglasses, but these are very special sunglasses. These block out almost all the light. There, I'll put the pair on right there. You wouldn't want me driving my car down your street with these glasses on. I can't see a thing. The only thing I can see through these glasses is the sun because it's so bright. Okay, and we use these glasses when the moon moves in front of the sun, and it blocks some of the sun's rays. That's going to happen April 8th, 2024. We're going to see the what we call a solar eclipse. And so this is a really good time to use these special glasses to look at the sun. These ones are a little bit more expensive, but we also have cardboard version ones as well. There's the cardboard version. Again, it's a safe way to look at the sun. Now, the other thing that you can do is that you can build yourself a pinhole camera. So I've got one here in the lower right-hand corner. And so this little boy here, he's taken a cardboard box, he's cut a hole in it for him to look through. He's cut another hole here. He's put a piece of tin foil over there, and he's taken a little pin. He's poked a little hole so that just enough light comes through there. Sun goes through that little pinhole and gets projected on the back of the box. So you're not looking directly at the sun. You're looking at a reflection of the sun, and that's a perfectly safe way to do things. Okay, so that's a cool project. You've got till April 8th, 2024. In Ottawa, about 90% of the sun's going to be blocked by the moon. And if you drive down to Kingston, 100% of the sun's going to be blocked by the moon. Now, you probably saw this in some of the earlier presentations. If you want to look through a telescope at the sun, the only safe way to do that is to either have a solar telescope, or you get a special shield like this. This is designed to block out 99.99% of the light. This goes over the end of my telescope, and this allows me to safely look at the sun. Now, some older telescopes used to have this piece. This fits into the eyepiece. This is the piece you look through. They don't sell these anymore. They're not allowed to sell them because they're very, very dangerous, okay? So, but some old telescopes still have these. And if you have one of these, I say throw them in the garbage, okay? Well, what happens is that a telescope takes the sun and it magnifies it, makes it much stronger so that you can see it in a bigger image. And that means the sun's rays are much stronger when they come through the telescope and they hit this black eyepiece. And when they hit this black eyepiece, it gets so hot that it cracks. And then next thing you know, you're looking directly at the sun and you're blind instantly. So do not use this. This goes into the eyepiece. If you have one of these, get your parents' permission and then throw it in the garbage. Okay, they're very, very dangerous. Okay, so we talked a little bit about the sun. Mercury. So Mercury is closest to the sun, and most of the time we can't see Mercury. It's because it is so close to the sun, but every once in a while, just after the sun sets, Mercury is visible in the sky. It looks like a small little star, but it doesn't twinkle. And in fact, this month, I can't remember the exact date, but Mercury is going to be far enough away from the sun as after the sun sets, you'll be able to see it for a little while. It's the smallest of the planets, and it's got no moons. Next planet is Venus. Venus is the brightest of the planets when we look up in the sky, and it's almost the same size as the Earth. It's got no moons, but Venus has a problem. It has runaway greenhouse gases. There's so many gases covering the surface of the planet, clouds and so on, that it's so hot that lead, which is a type of metal, is melting at the surface of Venus. Okay, so it's very, very hot and not a very nice place to live. Okay. Well, there's Earth. So there's the moon in front of the Earth. Okay, so it gives you an idea of the size. And you can also see the International Space Station. This is the largest of our satellites. Now, this number here is incorrect. I say lots of satellites, there's 5,000. This was about a year ago. We had about 5,000 satellites up there. 3,000 of them are dead, space junk. So about 2,000 active satellites. Well, we've got a bunch of companies that want to give internet to everybody on the Earth, and they're putting out hundreds of satellites every month. In about 5 or 10 years, we're probably going to have 20,000 satellites going around the Earth. And you may say, well, that's a really cool thing to have internet everywhere. But what happens with those satellites is that the sun comes down, hits the solar panel. This is how they get the power for the satellites. And then the sunlight gets reflected down to the Earth as a little pinprick of light. And it just looks like a moving star across the sky. We have enough trouble trying to look past our satellites that are going around the Earth right now without them crashing into our pictures, basically photobombing our pictures of the things in deep space. We've got 20,000 satellites going around the Earth. That is a major problem. So we are working with the satellite manufacturers, and in fact, they're looking at putting solar shades on their satellites so to block the sunlight from bouncing back to the Earth. Okay, so we got lots of satellites. Mars. Mars is an interesting planet. We just had a Chinese rover land there just in the last day or so. And of course, we have the Perseverance rover and the Ingenuity helicopter on that planet. And it is a really interesting planet. So it's a red colored planet. It's not very big. It's about twice as wide as our moon. It's got 2 moons. It's got Phobos and Deimos. And Deimos is like a regular moon. It sort of travels around the planet just a bit like our moon does. Phobos goes about twice the speed that the planet spins. And it's in a really wonky orbit. And at some point, it's either going to break apart or crash into the planet. Now, if it does crash into the planet, it's not a very big moon. Won't do a lot of damage. Might be a cool new crater or something like that. Okay. Now, Mars used to have, we believe, oceans and water and atmosphere. And then what happened was the magnetic fields that were generated in Mars billions of years ago stopped working. And then the sun's rays then stripped away most of the atmosphere and all the oceans, and now it's basically a desert planet. It does have a North and South Pole here, and there's some ice caps there. Okay, it's Mars. Oh, here's the asteroid belt. Now, this is a collection of rocks left over from the formation of the solar system. There's been a lot of different speculation about this, and the story I like to tell, and there's many stories about the asteroids, is that if you think about the way planets form, they started with one rock, and then the gravity attracted another one, and another one, and another one. That's one way the planets could be formed. And then gradually you got enough collection of things together that you had yourself a good-sized planet. Well, all these rocks here wanted to form themselves into a planet. But unfortunately, there was this big bully called Jupiter. Okay, and every time they started to come together, the gravity of Jupiter ripped them apart. And so what we have is this collection of rocks between Mars and Jupiter. I call it a planet wannabe. It wanted to be a planet, but that is the asteroid belt. And got to jump. It's Jupiter. There we go. So Jupiter is the largest of the planets. It's a gas planet. That means that most of the planet is just a big ball of gas. Now, in the very center of the planet, there is a bit of a core. But in theory, I could take a long stick and stick it all the way through Jupiter and come out the other side. If I were to stand on the edge of Jupiter, I'd be sucked right into the very middle of the planet. It's got 79 moons, but that's not the most of the moons out there. We do have another planet that has more moons than Jupiter. And this here is a storm. That storm has been going on ever since we first discovered telescopes. It's probably went on long before that. And about 3 Earths can fit inside this storm. That gives you an idea of the size of the planet. Okay, and we call that the big red spot. Saturn. So Saturn is another gas giant. This is my favorite planet. I love the rings of Saturn. They're made up of chunks of ice and dust that go around the planet here. 764 Earths can fit inside of Saturn, so it's quite a big planet. It's a gas planet. And it is the king of the planets when it comes to moons. It's got 82 moons. Largest moon of Saturn is called Titan. And we've sent spacecraft past Titan, and we've sort of looked at what it's made up of. And we think that it could possibly be able to support some form of life. It wouldn't be like humanoid type people, but maybe smaller life forms. Okay. Uranus. So Uranus is 63 times the size of the Earth. It's got 27 moons. It's another gas planet. But during the formation of the solar system, something bumped into Uranus. That's what we figured might have happened. Most of the planets spin this way. Not Uranus. It spins on its side. Okay. Uranus has rings like Saturn, but it's not quite as big. Okay. And it's a gas giant. And then the last of our planets is Neptune. So it's slightly smaller, 58 Earths in size. It's a gas planet, has 13 moons. It spins in the normal way. It does have rings, a little bit like Saturn, but not nearly as big. And I'm missing a planet. Well, it used to be a planet, Pluto. So Pluto, back in 2006, a bunch of astronomers got together and said, Pluto, you're too small to be a planet. We're going to call you a dwarf planet. In fact, there's a couple of dwarf planets in the asteroid belt as well. So that's why I don't include Pluto in my little story here. Well, I'm going to have to get Bob the Builder involved here, because this monster has mixed up our solar system. So I'm going to need your help putting Bob and I are going to need your help putting the solar system back in order. So let's see what the monster has done to the solar system. Holy cow, it is in the wrong order completely. So what is the very center of our solar system? Anybody know? It is.
Come on, folks, type in your answers.
Yeah, type in your answers. Yeah. The sun. Good job.
The sun. Exactly.
Good job. Now, what comes after the sun? What's the smallest of the planets? Okay.
Mercury by Aurora.
Mercury. There. Good job. Okay. Then the next planet after Mercury, it is the brightest of the planets, and it's got a greenhouse gas problem, and we call this one just waiting see if somebody can guess what the next planet is. It is.
I have. Monica says Neptune.
No, it's not Neptune.
Nope, it's not Neptune.
No, it is.
Another try.
If you think about the story, my something monster, it begins with V.
Oh, here we have Venus.
Venus, there we go.
There we go.
Okay, and then our favorite place that keeps us alive, where do we live?
Theodore, Earth.
Earth, good job. Okay.
Good job.
Okay, then after Earth, we have my very eager, what's the music?
Mars. Yes.
Mars.
Yeah,
good.
Good.
Okay. And then always, we've got the asteroid belt. Remember, the asteroid belt's between Mars and Jupiter. Oh, so what is the next planet? I gave you the answer. Next planet is Jupiter. You got it. Okay. And then my favorite planet, Saturn. Good job.
Saturn. Yep.
Yep. And this is the favorite one for kids, so they mispronounce it. Uranus, or as kids like to say, Uranus. Okay, and then the last one is Neptune. You got it. So there's our solar system. So thank you for building up the solar system for me. We're safe now. Okay, now we have shapes up in the sky. Over time, us human beings like to connect the dots. And we like to do that with the stars. And we call these connected dots constellations. So some of you probably know some of your constellations. So I'm going to show just the stars and see if you can figure out which constellation this is. Any guesses? See if anybody knows what constellation this is. Goes all the way up here and up here. Big Dipper, good job. So Jason got that one. So there it is. There's the Big Dipper. Now, a couple of interesting things about the Big Dipper. Way back in Roman times, the Roman soldiers needed a way to test the eyesight of their soldiers. And they didn't have the fancy eye charts and eyeglasses like we have now, but they certainly didn't want to give their soldiers a bow and arrow if the soldier couldn't see properly. They may end up shooting some of their own people. So what they did was they had the soldiers look up in the sky and look at the bend in the Big Dipper here. And they said, how many stars are at the bend in the handle of the Big Dipper? And if the soldiers said one star, They did not get their bow and arrow. There's actually 2 stars there. Okay, so that was a quick eye test that they used to do for the Roman soldiers. Okay, now this one's a little harder to see. I'll give you a clue. This is the North Star, Polaris. This is a star that sits right above our North Pole. So it's very useful if you get lost. You can find out which way is north. Anybody know what constellation this is part of? It's a similar name to the last constellation. It's smaller though. Okay, so this is the Little Dipper. Whoops. There we go. So there's the Little Dipper. There's Polaris, the North Star. It's right at the end of the handle of the Little Dipper. Now, this is a big W in the sky. This is the seat of an Egyptian queen. And does anybody know what this constellation is called? No, it's not Tiara. No. Okay, so I see Theodore got the Little Dipper. Good job there. Okay, this is Cassiopeia, or Cassiopeia. There's 2 different ways of saying it. Okay, so this is sort of like the chair that she's sitting on. And I noticed that there's a fuzzy blob up here that photobombed my picture. This happens to be the closest galaxy to us. That is the Andromeda Galaxy. Happened to photobomb my picture there. So that's Cassiopeia. Okay, now to find the North Star. The North Star is not very bright. It's an average looking star up in the sky. And I have a lot of trouble, and I do a lot of looking up in the sky. I have a lot of trouble trying to find Polaris. But I know if I find the Big Dipper, and I draw a line all the way from the Big Dipper all the way up to this point here, it's going to tell me that that is Polaris. And if you think about it, Ottawa is halfway between the equator and the North Pole. So the North Pole's up here, the equator's down here, and we're about halfway. So if the North Pole's, if we're halfway, that means that Polaris is halfway up in the sky. It's another way to make sure that you're looking at the North Star. Okay, another story. Back in the slave trade times, when they had slaves in the United States, they often would want to escape to Canada where we didn't have slavery. And they would go from safe house to safe house all the way up to Canada. And then you knew the fastest way to get to Canada was to go north. Back in those days, they knew this as not the Big Dipper, but as the pouring gourd. A gourd is like a small pumpkin that's been hollowed out. You put water in it. And so the slaves were told to follow the water in the pouring gourd. So the water pours this way, and they go this way, they're going north. Okay, so that's a little story about the Big Dipper or the pouring gourd. Okay, so this is a wintertime constellation. This one is pretty well setting with the sun these days. But anybody know what constellation this is? This is a belt of somebody. Anybody know what constellation this is? Orion. Good job, Andrea. Okay, so this is Orion. And there's his spears, there's his shield, and there's the belt of Orion. And in the skirt of Orion, we got some really neat clouds, basically interstellar clouds where stars are being born here. There's the Orion Nebula. And up here, Orion's got a big red giant star called Betelgeuse. And back in the end of 2019, this star started to get dimmer and dimmer. And when a star starts to get dimmer, that means it's dying. And when a star dies, particularly one this size, it's going to go kaboom, and we're going to have what we call a supernova, which would be a spectacular event. In fact, it would be so bright we could even see it during the daytime. So we're getting really excited as astronomers, thinking, oh, maybe we're going to see a supernova of this particular star. That was the end of 2019. Then we came into 2020. Along with the pandemic, we ran into another problem. Betelgeuse started to get brighter again. And so all of a sudden it's back to its full brightness. We're not really sure what caused it to dim. Some people have speculated that there was some interstellar dust or something that moved across the face of it, but it's not going to blow up anytime soon. So we're going to have to wait for another supernova. Okay, now one of the handouts that you got is a star finder. And this is a really useful way to figure out where the constellations are up in the sky. Now, what you need to do with this is you download these from the website, and you need to print it on two pieces of paper. Don't print it double-sided; it won't work. So, one piece of paper, you're going to need to cut it out. There's what it looks like after it's been cut out, and you can see there's 1, 2, 3 tabs. So, I'm going to turn this around, and I'm going to fold those tabs in. This is going to be the pocket for the other piece. Okay. So there is the star finder. And then inside that pocket, I've cut out the other circle, and I'm going to put this into the star finder. Okay, so that's how you put it together. Very, very simple. What I do is I put Scotch tape on the back corners here to keep it together. So I've got one I've already put together with Scotch tape. It's a little bit easier to work with. And what I have to do now is I know that it's May the 15th. So let me just, I'm going to dial May the 15th at 9 o'clock. Just a second here. And I can't see whether I'm in focus or not, but basically I've dialed May the 15th at 9 o'clock. The picture that you see on your screen here is on March the, let me see, March the 16th at 9 o'clock. Okay, so you can see here, it might be easier for me to show you on this screen at 9 o'clock, okay? And then what I do is I have to know which way is north. How do I find north? Well, I've found the Big Dipper and I found Polaris. I know which way is north. Now I'm inside right now. I'm in my office and I happen to know that north is behind me. So I'm going to take my star finder. I'm going to dial the date and I see where it says Northern Horizon. I'm going to pick it up and I'm going to look up, and now I can see where all the constellations are for that particular time. Now, one of the challenges that we have with these is that I will give these to folks when we're doing stargazing, and it's nice and dark out there. My eyes have got adjusted. I can see a lot of cool things. And what do the folks do? They bring out a bright white flashlight, and I've lost all my night vision. Oh, it's terrible. And then they shine this on here, and they look at this. Then they look up in the sky, and they can't see anything. Well, what you need is an astronomer's flashlight, and you can spend a lot of money doing that. But you know what I do? I went to the dollar store, and I got this. I think these are $1.25. That included the batteries. That was a pretty good deal. I picked up 2 of them. I picked up this one, but this one, I went and I got a red Sharpie, and I colored in the lens. You can see now that this is a red flashlight. Okay, this is really good because it protects your night vision. Just the red light is good for that. If you don't have a red Sharpie, if you've got red nail polish, it works just as well. And when I go hiking with my scouts, I will often have them carry red flashlights when we do our night hikes because they don't lose their night vision, and a red flashlight lights up the trail just fine. So for $1.25 and a Sharpie, you've got yourself an astronomer's flashlight, a great way to look at the star finder. Okay. So moving on. The other thing that we have in the handouts here is this thing called the Evening Sky Map. And this is a really good resource. It comes out once a month. It comes out at the last day of the previous month. So on May the 30th, 31st, thereabouts, go to skymaps.com and you can download this. This is the one for May. So we are on the 15th of May. You probably heard that Ramadan was over, okay? And Ramadan ends on a new moon, which is the 11th. So a new moon is where this moon is on the same side of the Earth as the sun. You really can't see the moon at that point. And then we're going to move towards a full moon, okay, on the 26th of the month. And this tells you various other things that are happening as well throughout the month. And what I like about it is that there's a planet in the evening sky, it's going to show it. So right now, Mars is about the only planet that we can see in the evening sky at the times that they have here, okay? On the back of it, then they have the Northern Hemisphere, what you can see with the naked eye, what you can see with binoculars, and what you can see with a telescope. Cool things to see, and some of the glossary, some of the things that we say when we're talking about astronomical things. Very good resource. Again, it's free. Skymaps.com. Go ahead and download it. The other thing you're going to have on there is this is a list of various astronomy websites. And so I'm part of the Royal Astronomical Society of Canada, the Ottawa Centre. This is our website. We have the Ottawa Valley Astronomers. We've got Astro Pontiac. We've got Ottawa PopScope. We've got a website that you can go to that tell you what the cloud cover is going to be. I went to that today, and this evening it's going to be a bit hit and miss when we come to doing our observations. But this gives me an idea of whether or not I should drive 2 hours to go out and look at the skies. This is a really good area for dark skies. It's near Plevna. It's about an hour and a half from here, the other side of Perth. And they've got a nice concrete platform, even have a porta potty out there, and they've got power. So if you've got a telescope that needs power, perfect spot to go. Really nice dark skies. If you want to find out when the International Space Station is coming overhead, this is a cool website to go to, heavensabove.com. And you got to make sure that you set your location properly. It assumes you're off the west coast of Africa, which isn't very helpful. But if you go in and you say, I'm in Ottawa, then it's going to give you the correct information for Ottawa. This is a voice of experience here. I went in there one time to do something, forgot to put it in Ottawa, and I got really bizarre results. I couldn't figure out what was going on. And then I looked to see where it told me I was, and I figured it out. Sky Maps, that's what we just talked about right here, skymaps.com. Sky News is a Canadian astronomy magazine and comes out every 2 months. It's published by the Royal Astronomical Society of Canada. And when they reopen, you can get these at your local chapters, places like that. Now, this is one of my favorite pieces of software. This is absolutely free. You can put, this will go on any PC, Mac, or Linux system. And it is a planetarium that you can load, and you can take a look at the night skies. And I'm going to show you that in a couple of minutes, okay? Now, the other thing I always like to sort of finish up with this section on is, if you want to buy a telescope, please do not go to Walmart and buy the $39.95 special. You get what you pay for. You want to deal with somebody who knows what they're talking about when it comes to telescopes. And we're really lucky. There's about 4 telescope stores across Canada, and we've got the best one in Ottawa, Focus Scientific. They're sort of closed right now, although they're very good at, like, you can talk to them through their website. They're at Merivale and Bentley Road, and they're excellent for their support and service. I've used them a lot of times for my telescopes. And talk to them if you want to get started in astronomy. And, you know, a starter telescope, $150 up, something like that. You can spend thousands of dollars, but you know, you can probably get a decent starter scope, you know, $150, $200 in that price range. And these are the guys you want to go to, because they're not going to oversell you on anything. They're going to be quite honest and say, okay, here's what you should do. This is one of the handouts that you have that you can download. You can cut those up and rearrange them and try to get the planets back in order. And telescopes. So we have a variety of different types of telescopes we use as astronomers. And basically, when it comes to telescopes, a very sort of rough rule of thumb is the bigger the opening, the longer the tube, the better the picture. Okay. So this little telescope here, the light comes in all the way through to the bottom, bounces off the bottom here, pops out the eyepiece. And this doesn't look like a very big telescope, okay? So this one would maybe be good for looking at the moon and maybe some of the bigger planets. You're not going to see a lot of detail. So the folks who are designing telescopes said, okay, how do we make that tube longer? So what they did was that they put a mirror in the bottom here. So what happens here is the light goes all the way down to the bottom, all the way back up, and comes out the eyepiece. So that's like I've got a telescope that's twice as long as this, okay? And then this one here is the same as this one, except it's bigger. This one, you need to maybe get on a step ladder to look through it when you're looking straight up in the sky. This is sometimes could be almost 2 meters off the ground. Light comes all the way to the bottom, bounces off a mirror, comes all the way back up, and comes out the eyepiece. So this actually sits on the ground. So this one here looks like it's got a telephone on it. Well, this is a computer keypad, and this is what's called a go-to scope. So with this telescope, what I can do is I set it up and I get it all aligned. I tell the telescope exactly where I am in the Earth, and then I push a couple of buttons and I say, I want to look at Jupiter. It goes, and it goes up and looks at Jupiter, and as the Earth turns, as Jupiter moves, it tracks it across the sky. Otherwise, for the other telescopes which I have here, I have to adjust them about every minute or so because the Earth is turning. And then the last type of telescope we have here is a radio telescope. So these are in the visible spectrum, what we can see with our naked eye, but there's a lot of things that come in on the radio spectrum. And this is Really cool thing. This is the 4th largest radio telescope in North America. It's in Algonquin Park. It's the Algonquin Park Radio Observatory. And my dad was one of the first scientists to work on this back in the mid-60s. Oh, I've got some noise going on here. Just a second. There we go. So I want to talk to you a little bit about rocks from space. So as the Earth goes around the sun, it encounters clouds of dust and rocks. And as these rocks come into our atmosphere, they burn up. And we get this thing here. Okay, it just looks like goes across the sky. This is called a meteor. And sometimes we go through a big cloud of dust. We have what we call meteor showers. So we see many of these happening all at once. If a meteor makes it all the way through, it doesn't burn up in the Earth's atmosphere, it hits the Earth, and we call it a meteorite. Now, this is a meteorite. This is what's called an iron meteorite. This one landed in Argentina, and I actually have a piece of this. This is a iron meteorite. This is a rock from space. Okay, and but it's a magnetic because it's iron meteorite. It sticks to my magnet. So I'm holding there a rock from space. That's a really cool thing. When I do these in person, I hand this around so the kids can hold a rock from space. Well, let's move on here. What happened to the dinosaurs? Well, a big meteorite landed off the Gulf of Mexico. It was about the size of the city of Ottawa. And as it hit the Earth, it pushed a lot of water vapor and dust up into the Earth's atmosphere, and it blocked out the sun. And the sun killed off a lot of the vegetation that either the dinosaurs ate or the animals that the dinosaurs ate, and wiped out the dinosaurs. Okay, so that was a huge meteorite. And I just realized I forgot to turn on my computer sound, so I'm just going to stop the share for just a second here. Sorry about that. Share sound, go back in. There we go. I've got a video coming up and I realized you're not going to be able to hear it. Okay, so this is the a meteor. This is what the dinosaurs saw. Absolutely huge one. And look at this. This is the crater in Arizona. Are these guys ever lucky? The meteorite missed them. Actually, this was a visitor center that was built after the fact. Okay. Anyways, this is a big crater here on Earth. Anybody know where this was taken? Any guesses? It wasn't on Earth. This is a crater on the moon. There are some more craters on the moon. So the moon doesn't have any atmosphere. So anything that flies towards the moon doesn't get burned up and it hits the surface of the moon. We've got lots of craters on the moon. And there is a crater right there. There's Tycho. And that's a new crater. It's only about 95 million years old. Brand new. Well, brand new from astronomical terms, okay? A couple of things to note on the moon here. We've got the Sea of Tranquility, which is right here. This is where the first person landed on the moon back in 1969. And the last person to step on the moon was in the early 70s. So we are sending folks back to the moon. And in fact, somebody's going to be talking to us about that coming up at 4 o'clock today. So here's a picture of the moon. You can see all these ejector rays. So when the rock hit the moon, all the stuff got spewed out. Okay, so that's the crater Tycho. Oh, where's the next slide? So I'm going to show you a short video here, how you can make your own craters.
Hi, we're here today with a fun and educational activity that you can do at home,
really cool exercise. Whoops. There we go.
Hi, we're here today with a fun and
I'm not getting. You guys getting any audio there?
At home, at school, or
okay.
Yes, we have audio.
And it involves making craters. Go outside tonight, take a look at the moon, and you'll see these circular features with lines coming out. Those circular features are craters, and the lines coming out are ejecta patterns, rays. The way those craters were formed were from rocks coming from outer space and smashing in to the surface of the moon, pulverizing the soil there, what we call regolith, and spraying it out along those ejecta pattern rays. You can make your very own craters. You start with about 1 inch of some flour, spread out nice and smooth, and then take something that is of color, like these are little cake sprinkles, and kind of just sprinkle them evenly over the surface. Then you need another layer, and what we've selected is cocoa. You can sprinkle it with your spoon or sift it over the top, which will make a more even surface. To simulate a rock impacting a surface, drop them from a reasonable height. I'm going to use this big rock first. As you can see, this impactor made a very nice crater. This indentation is the crater. The impactor, the rock, is outside because it actually bounced out. That happens sometimes in real life. And you see that it threw out a bunch of the subsurface material. And we have our own little geologic excavation. The white things coming out, those are the rays, just like you see on the moon. And some of our sprinkles got thrown up, and that represents the mineral diversity of the surface that was impacted. Not all meteorites come in perpendicularly. Sometimes they come in at an angle. Take it and kind of chuck it at an angle. You see that the ejecta pattern is a little bit different. Notice there are no ejecta rays on this side, they're all on that side. From looking at a crater, something we can tell is what sort of angle the impactor came in at. Remember, you can experiment by trying different layers of materials to put down in your pan to impact with different rocks. You can use different size rocks. You can try dropping from different heights or throwing at different angles. And then take a look at your ejecta patterns and see what that tells you about the crater. So have a good time experimenting.
Okay, so there's how you can make your own craters at home. So what I'd like to do now is I'm going to run this software called Stellarium. Remember, this is an absolutely free software, stellarium.org. You can put it on your PC or your Mac or your Linux system. I don't think there's a version for Chromebook, but certainly the Mac, PC, and this is a really cool piece of software. I'm going to stop the share for a second here, and we're going to take a look at the night skies. And what I like about this is it's never cloudy. So this is what Ottawa looks like right now. Spin around here. There's the sun. And I'm looking south. And what I'm going to do is, it's more interesting when it's darker skies so we can see something. So I'm going to move the time forward to about 9 o'clock tonight. Let's.
Dave, you're not sharing your screen at the moment.
Oh, I'm not. Okay, just a second here. Oh, I probably. Yeah, sorry, that was. I started the app. Just give me a second here. Thank you for that. I clicked directly on the app rather than the share screen. So give me a second here. Okay. Let's try that again. Okay. Where are we at here? Okay. Share screen. Stellarium. Share. How's that? You can see it now?
Yes, we could.
Okay, super. Okay. Sorry about that, folks. So this is Stellarium. So this is what Ottawa looks like right about now. And there's the sun. But I'm going to make it a little bit darker here. I've got a lot of superpowers when it comes to this software. So I'm going to make it a little bit later. Make it about 9 o'clock tonight, so it's nice and dark. Now, one of the other superpowers that I have here is that I can freeze time. The reason I'm going to freeze time is that if I try to zoom in on something, it will start moving as the Earth turns, and that sort of gets in my way. So I'm just going to freeze time. Oops. Date and times is still moving. Yeah. There we go. So now I've frozen time. That's going to make it much easier for me. Now, what do we have up in the night sky? Well, first of all, let's turn on the constellations so we can see what's up there. And I'm going to turn on their names. There we go. And now I can see the constellations. Oh, and look, the Mars and the Moon are very close together tonight. Let's zoom in on those. So remember, we just had a new moon on the 11th, so the moon is just growing in size. So there's what the moon is going to look like tonight. And there's Mars. Mars is up every evening. You'll be able to see it through most of the evening. Okay. So remember I said Mars has two moons, Deimos and Phobos. Phobos goes around Mars twice as fast as Mars is spinning. It's got a really wonky orbit. It's going to break up one of these days. Then this is the regular moon. So that's what Mars would look like from here. Let's zoom out a little bit more here. Oh, and they're right in the constellation Gemini. Okay, so these are Gemini twins. We'll just turn on their picture here for a second. There they are. Okay, so they're right in the middle of Gemini. That's constellation. So we use these constellations like signposts so we can find other cool things up in the sky. So I'll zoom out a little bit more here. So remember I talked about the Big Dipper. Well, the Big Dipper is part of a bigger constellation called Ursa Major. Just a second here, zoom out a little bit. Ursa Major is the big bear. So there's the bear's nose, there's his feet, there's the bear's tail. And then there is the Little Dipper, Ursa Minor. So Ursa is bear, Minor is small. So big bear, little bear, okay? And remember, if we want to find Polaris, we just draw a line right off of the Big Dipper like that. Remember I talked about the Roman soldiers and their eye test. Let's take a look at the bend in the handle of the Big Dipper here. There are the two stars, Alcor and Mizar. Okay, so those are the two stars they had to be able to spot. Let's keep on going, looking around here. Zoom out a little bit. Whoops. Sorry, hopefully you're not getting too dizzy as I move things around the screen here. And then by using the constellations, I can then I can sort of know where things are in the sky, because sometimes there's some really neat deep space objects that I can go to. So for example, I zoom in here. Look at that. So that is a galaxy. It's actually two galaxies. They're interacting with each other. Okay, and I knew that because it was off of the end of the Big Dipper. So zoom back out here. So there's the end of the Big Dipper, and I knew if I went off it there, I would find that galaxy. Okay. Let's see what else we've got here to see. Okay, so what I'm going to do is I'm going to move the time again. I'm going to move it to the middle of the night. There's Cassiopeia. Remember the big W in the sky? Right there. And I think it's hiding behind the tree here, but we have Andromeda. So I'll have to, I'm going to move the time forward now, way past our bedtime. Let's move it to about, let's move it to about 4 o'clock in the morning. So there's Ursa Major, Big Dipper. Okay, there's Cygnus the Swan. So there's the swan, there's the arms of the swan, there's the tail, there's the neck. And this is Lyra. Vega is one of the brighter stars in the sky. Okay, so you can, it's almost directly overhead at this time. But I know that if I find Vega and I find Lyra, I go right off of Lyra here. There is the Ring Nebula. Okay, so this was a star that went supernova a long time ago. It exploded. There's all the gases left from it. And then this is all that's left. It's a little white dwarf. Okay, so that's called the Ring Nebula. Now, this is what might happen to our sun. So our sun, 5 billion years from now, it's going to start growing. It's going to become what we call a red giant. And it will grow and it will get so big that it will probably eat up Mercury, Venus, Earth, Mars, maybe part of the asteroid belt. It's going to get really, really big. And then it's going to shrink into a white dwarf, and it will probably explode into a supernova, potentially. Okay, so that's good. What's going to happen to our sun. Don't need to worry about it. It's billions of years away from us. Okay, by that point, if we're still around, we probably will have invented spacecraft that can go to other solar systems, and we can find another safe planet to go to. Okay, so Any questions for me?
Yes, there was a question raised earlier about safety.
Mhm.
Are welder safety, welder shades good for observing a solar eclipse?
Yes, certain ones are. Your best bet is to Google what type of welder shades to use, but I don't typically use those because I don't know the different types of welders' glasses. But there's Google. You'd have to Google and find out which is the recommended one to use. I always like to use the ones that I showed you here, and they're relatively inexpensive. You can order them online, but make sure you order them from a reputable place. There's some that come from China that are not very well made, so you got to be very, very careful when it comes to the solar shades. There's a company called Rainbow Symphony in the States that they're the biggest manufacturer of these shades, and I know their shades are properly made, so that is a safe way. So you can see now in the middle of the night here, I can see two other planets. I've got Jupiter and Saturn. So let's zoom in on them. Now with a small telescope, or even with a pair of binoculars, we can see the four largest moons of Jupiter. Remember, Jupiter has 79 moons. So we've got Ganymede, Europa, Callisto, and Io. And Europa, they think there could be life in Europa. They think there's a big ocean on there. Let's zoom in on Jupiter. Oh, I do not see the red spot. Where do you think the red spot is? Any guesses? What happened? What does the Earth do? The Earth turns, so Jupiter turns, and so the red spot's on the other side of Jupiter right now. And every once in a while, you'll see a black spot on Jupiter, and that is when it's basically like a solar eclipse. One of the moons is blocking the sun, and you can see a black spot go across the face of Jupiter. So there's Jupiter. I'll zoom out a little bit. Keep going. And there's Saturn. So there's Titan. That's the biggest moon of Saturn. And there are the cool rings of Saturn. And even through a small telescope, and I have what do I normally take with me? I think it's a 3-inch telescope. I can actually see the rings of Saturn, not in a lot of detail, but even with a small telescope, you can see the rings of Saturn. You can see that there's some breaks in the rings here. This is called the Cassini division. And I think this outer break in the ring, there's actually a moon that sits in there. It's probably on the other side of the planet. There's Saturn. It's a big gas giant. Okay, so sometimes when you want to see something, you got to get up in the middle of the night. Now, what is happening is that as time goes on, as we move later into the summer, Jupiter and Saturn are going to be visible in the evening sky. So by the end of July, you'll be able to see Jupiter and Saturn in the evening sky at a reasonable time. But remember, at that time of year, it's going to be brighter much later in the evening. So you still have to stay up reasonably late. What you see right here is the Milky Way. So we're looking right into the center of our galaxy. Okay, and somebody had asked a question about, well, I guess somebody's already answered it, about whether we can see some of these nebulas from here. Absolutely, you need a dark sky location for that. And let me see whether or not Andromeda is up. Yes, it is. So I'm going to go here in Andromeda. And this is the closest galaxy to us. In fact, it's moving towards us. Okay, this is a spiral galaxy. It looks probably a little bit like ours. This is Andromeda. In the very middle of this galaxy, there's a massive black hole. And it's moving towards us. Eventually, it will merge with our galaxy. And when the galaxies merge, not a lot will necessarily happen because there's so much space between all the stars. There'll be some interaction, particularly between the big black holes here. But it probably won't impact our solar system, particularly when the two merge. But we're talking billions of years from now. This is millions of light years. So if you had a spacecraft that could travel the speed of light, you still have to travel millions of light years to get here. So we're likely never ever going to be able to visit that that particular galaxy. Okay, any other questions for me?
I just wanted to mention that that the Andromeda Galaxy is an excellent binocular target, especially if you're at a dark sky. Like I was a number of years ago at Plevna, it blew me away. Just putting the binoculars on a tripod and to see M31, it was truly amazing.
Yeah, yeah. From Ottawa, or even from where we often have our star parties out at the Diefenbunker, this is just a gray, fuzzy area.
Yeah.
We get into a really dark sky location. It's absolutely amazing.
Yeah, it really is.
Yeah. Okay, so I'm doing quite well time-wise here. So if there's no more questions, hopefully you'll be able to download your Starfinders and put them together. And yeah, they're a really handy thing to have. And what I sometimes do is when I go out stargazing is I just take this with me. So I can find the Big Dipper on here, then I can just use this as my starting point. And remember, the constellations are like little signposts up in the sky, so we can find other really interesting things there. Okay. So we've got.
Yeah. Well, thank you. We have a few more minutes. I think Jim is on next.
Yeah.
And
I'm just going to remove my spotlight. There we go. And
okay. All right.
Jim Thompson. Let me see if he is.
I think Jim is waiting in the wings.
Okay, I'll make him spotlighted. There we go, Jim. You are muted.
Great, thank you, Dave. All right. The plan for the next 20 minutes or so was to provide you with a live view of the moon, which is actually up in the sky right now. It's not that far behind the sun, making its way across the sky. But as you might imagine, it is cloudy. So our backup plan is to show images that were pre-recorded. So I'm just going to share my screen. I have 3 images of the moon to share. These are all images that I captured myself from my backyard. And I've selected these 3 particular pictures because they are phases of the moon that you might not necessarily look at that often for various reasons. So for example, this here is a view of what the moon roughly looks like today. Maybe more so tomorrow, but this is roughly what it looks like today. It's a fairly young, we'll call it a waxing crescent moon. So waxing means it's getting larger, like there's more of it's being illuminated from our perspective. But it's following the sun fairly closely. So you don't actually see it very well during the daytime because compared to the sky, it's not very bright. You would really only notice it at sunset if you happen to be facing west, and then it would really stand out. So I thought that this would be a good opportunity to allow people to have a closer look at what the moon looks like this time of the month. So I'm just going to zoom in a little bit here so we can get a closer look. So as Dave mentioned earlier, the moon is covered in thousands and thousands of craters. So all of these circles that we see are due to impacts. Now, there are some places where the circles are in fact volcanoes, but what we're seeing here are pretty much all craters. I'm going to zoom in a little bit more and we can get an even closer look. So you can see the craters vary greatly in size. The belief currently from scientists is that the largest craters are older than the youngest craters, although there is some, there are exceptions to that. But in general, earlier in the solar system's history, the things that were whizzing around, impacting into the planets and the moon were larger in size. But eventually all those large objects were scooped up by the planets and only smaller objects remain. So the smaller craters tend to be younger. Now you'll also notice that there are flat areas of the moon and there are bumpy areas of the moon. So the bumpy areas of the moon tend to be older. They are some of the original crust, like if we look at an annotate tool out here. So this kind of a raised area here that's got lots and lots of craters on top of each other, that is a relatively old part of the moon's surface, part of the original crust. But then this smooth dark gray area here and down here that we call mare or seas, because at one time people thought they were actually a liquid. This is back hundreds of years ago. But they are, in fact, plains where there has been lava on the surface that has flooded a depression, usually a very large impact basin. They've filled up with lava and then cooled. And so these areas are younger. The flooding of the lava occurred later in the history of the moon. That's why we don't see very many craters, and most of those craters that we see in the mare are smaller in size.
That's pretty good.
So we're just going to mosey on down. Before I mosey on further south here, just some, for your own understanding, directions on the moon, if you were looking at a map or somebody is explaining where things are, when you're looking at the moon with your naked eye, the right-hand side is east, the left-hand side is west, the top up here is north, and the bottom down here is south, just for your own information. So I just went down a little bit further south to this very striking area of the moon. If you have binoculars and you catch this phase of the moon when the terminator or where the shadow is in this area, it really highlights this particular part of the moon. I'm going to zoom out just a tad so you can see better. So this is an interesting image because it kind of gives you an idea of the scale upon which the impacts have affected the moon. So I think you can fairly clearly see that there is a line of cliffs along here, and that actually it goes all the way around. There's a remnants of it here, there's remnants of it up here. So that is actually the outer edge of a very, very big crater. It's so big that there are rings on the inside. It's a property of impacts, not just asteroids on the moon, but any type of an impact. Depending on the size and the energy involved, you start with a crater that looks like a bowl, and then as it gets bigger, you get a central peak, like you see on these ones up here. There's a central peak there, central peak here. And then as the crater gets bigger and bigger, that central peak becomes a ring. And that's what we see on this large impact basin. So that's some interesting things to see during this particular phase of the moon. Now, moving on to a second image. Another time of the month that people rarely look at the moon is the full moon, surprisingly. You know, it's obvious when it's a full moon because it's very bright outside in the evening. It illuminates, you can do stuff outside. But people don't really look at the moon very much during this phase because they don't think it's very interesting. And I don't think that that's really true. You can learn a lot about how the moon was formed by looking at it during this particular phase. And I'm going to zoom in and kind of show you what I mean. So let's take this area of the moon here, for example. So this crater that I've got in the middle is crater Copernicus. I think it's about, is it 85 to 100 kilometers across, something like that. So if you remember from the video on making your own crater that Dave showed us, they talked about rays, ejecta rays, and you can really see those rays during a full moon. Because this material has been dug up from underneath the moon's surface, it's a bit younger. It hasn't been darkened by the sun, so it's brighter in appearance when you see it on the surface. That's why the rays are lighter than the darker mare material underneath. And you can really only see this well during the full moon. You can also see, if we go up here, and I'm going to zoom in all the way to 100% so we get a really good look. You can see this crater right here. It is very bright. It really stands out, not just in photographs, even through binoculars. This crater stands out as very bright. Well, that crater being bright compared to, say, maybe this crater over here, that tells me that this crater is much younger than the darker crater. Over time, this material, the bright material that has been exposed from the impact, it will darken over time. You know, we're talking millions of years. So this tells me any crater I see that's bright, it is much younger than the other craters around it. So that's kind of an interesting thing that you can also see very well on a full moon. Another thing that I find neat, and you kind of need a telescope to see this, is to go down to either the South Pole or up to the North Pole. I'm just going to fly down there. Is during the full moon, it is a great opportunity to really see and appreciate how tall the mountains and how deep the craters are, what we would call the topology of the moon. So because we're looking at the moon at a shallow angle and the sun is illuminating it in the way it is, you can really see how the mountains stand out. For example, this peak right here. And there's another big plateau right here. There's a whole chain of mountains here that are very difficult to see during any other phase of the moon, but this time of the month, they stand out quite well. And we'll find out a little bit more about this particular part of the moon because this is where they're talking about sending the Artemis mission, having a permanent manned base on the moon is on this part of the moon, and we'll find out more about that later. So see, we have a question from Jocelyn. I'll just go ahead and answer it because it's sort of pertinent to what we're talking about. So how does the sun darken the moon? Well, as we learned earlier today, the sun generates a lot of plasma, and so there's a lot of positive and negative ions that are being thrown off the surface of the sun. Some of them get caught in the magnetic field lines and get pulled back, but a lot of it continues out into space. And we call that the solar wind. It's just a constant stream of charged particles. On Earth, we're protected by our atmosphere and our magnetic field, so we're not really affected by it. But if you are a body that doesn't have an atmosphere or magnetic field like the moon, then you're constantly getting bathed in charged particles. And it's that bombardment with charged particles that over time causes the moon to be dark. In fact, the moon looks fairly bright in these images, and when you look at it in the sky, it seems bright to your eye. But if you were to have a piece of the moon with you here on Earth, it would look as dark as asphalt. It's actually, in relative terms, quite dark. It's just that it's being so brightly lit that it appears bright to us. Okay, I got about 9 minutes left, so I'm going to do one final image. And this image is another image of the moon in a phase that we don't often look at because it's not really very convenient to. This is the waning crescent moon. So this is in the latter part, approaching a new moon. And the moon here is leading the sun, so that you would only see this phase in the morning. In this particular case, I captured this image. I got up at 4 in the morning to go out and capture it from my backyard before the sun came up. So that's not a convenient time for people to go out and look at the moon. Maybe if you head to work early, you might see it. But to really observe it nicely, you need to get up in the middle of the night to see it. And that's a shame because there are a lot of very interesting features to observe during this phase. There's a lot of contrast between, I'm going to zoom right into 100% here. So again, this is an image I captured from my backyard with my telescope set up. So there's lots of lava flooded plains here. This big region here is called Oceanus Procellarum. It's the biggest continuous flooded region. It takes up most of the western side from our perspective of the moon. And because there's so much lava here, there's actually quite a few volcanic features that we can see. So if you see these two domes right here that look like just very tidy looking mountains, those are actually volcanoes. The Gruithausen domes, or Gruithausen, it's hard to say. So those are volcanoes. And there are many other volcanoes in this area. I don't know if you can see it, but there's kind of a lumpy thing over here. That is a massive shield volcano. It's actually an area of multiple volcanic domes that have just kind of conglomerated into one big lump. So very, to me anyways, fascinating to think about a time in the moon's history when there is lava flowing out of these fissures, flooding across the plains of the moon. That would have been something to see if we were around, a couple billion years ago. Continuing south, even more volcanic features. So if you see this sort of a crater here, that is a caldera from a large mountain. So this whole uplift here, this diamond-shaped uplift, that is uplifted because it's a volcano. It's been pushed up by the lava underneath. And this channel is where the lava flowed. So this is like several hundred kilometers long channel, and it actually extends all the way out into the plain. This is called Schroeder's Valley. It's if you have good clear conditions, it's really a fascinating object to observe. And there are a lot of other smaller type channels, like there's a one there, here. So those are all related to the volcanic activity in this part of the moon. We got 4 minutes left. I'm gonna zip on down. Oh, we'll make a quick stop here. This lumpy area, all these bumps, each one of those bumps is a volcano. They're on the order of a couple hundred meters high by a couple kilometers across. These are called the Marius Hills. So there's, dozens and dozens of volcanoes in that field. Very, very cool. So lots of things to look at here, but because I have 4 minutes left, I'm gonna zip down to here. So this is another one of those large impact basins I told you about that has since been flooded with lava. We can see how smooth the floor is. The craters that are in it are quite small in size. But what I find fascinating is the crater in the sort of in the 1030 position. That's crater Gassendi. It's named after a French astronomer. I'm going to zoom in. I'm at 100%, but I'm going to go to 200% just to give people a better look. So in a telescope, this crater is quite fascinating. There's so much detail to see. So this crater at some point had its floor heaved up, presumably by movement of lava underneath. And by pushing up the center, it caused all of these cracks, all these fissures. So yeah, definitely a fascinating target. There's a similar crater all around the rim. There's with cracks in them because of being deformed by what's going on underneath the crust. So really fascinating phase of the moon to observe if you are able to get yourself out of bed in the middle of the night. And that's it for me. I don't know if there's any questions.
No questions noted here so far.
Well, Jim, if you have a moment.
Sure.
Let's see. So Jocelyn Gill asked, so does this radiation change the chemical characteristics of the mineral to something darker? Asking about particles coming from sun.
That is a good question. I don't know if Simon knows the geology associated with if it's a photochemical reaction that causes the darkening.
Yeah, I can. Can you hear me?
Yeah.
Okay. Yeah. What's happening is that the bonds in the minerals, the bonds between the atoms that make up the minerals, those are being broken. And so light no longer goes through or reflects back from the minerals as it did before they were damaged, but the same elements are still in place. It's rather like the difference between sand, which is made of quartz. If you melt the sand, if you heat it up, it turns into glass. It's still the same composition, but the optical properties have changed. And it's a similar kind of thing. You've got the same composition chemically, but you change the physical nature.
All right. Thank you, Simon. Now, was Olaf successful in getting connected as a panelist? I noticed that she was asking about that.
Yes, I was, Jim. Thank you.
I see her.
Excellent. Excellent. Okay, well, I will hand the reins over to you. I believe I am now the co-host. So did you want questions for the end or through the talk?
If there are questions during the talk, I'm happy for you to interrupt me. Yes.
Okay. So, okay, that's where we'll run it. So I will spotlight you. And you're sharing your desktop, so take it away.
Hello, bonjour, Annie. I am very happy to be celebrating International Astronomy Day with all of you and with the Royal Astronomical Society of Canada, Ottawa Centre. Thank you, Jim, for that awesome exploration of the moon. I very much enjoyed that. I am streaming from Sudbury, Ontario, which is in the traditional and ancestral lands of the Atikameksheng, Anishinaabeg, and Wahnapitae First Nation. We are in the Robertson-Huron Treaty area. If you're joining us live right now, please share where you are right now. And if you know the traditional and ancestral lands that you are on, whose lands those are, or the treaty that you're part of, please share that as well. I always love to hear that. Okay, so I absolutely love Earth, and I'm sure you do too. And you know what, so does every astronaut who has ever looked back on this beautiful blue sphere from space. There are so many quotes from astronauts about taking care of our planet and how precious it is. But I can think of a place that's not Earth that would be very nice for astronomy. If you can think of a place that might be very nice for astronomy, go ahead and share it in the comments. So I'm thinking of a place where there's very little atmosphere. So how many stars would you be able to see? And how bright would they be? Imagine there would never be a cloud in the sky. And that night would last half a month. Be pretty good for astronomy, huh? And yeah, of course, I'm talking about the moon. But that's just one reason we want to go back to the moon. And today I would like to share the global space community's plan to go back to the moon and beyond. And I'd also like to share Canada's role in this mission. But first of all, let me introduce myself. My name is Olathe McIntyre, and I'm a staff scientist for Spaceplace and the Planetarium at Science North here in Sudbury. So this is where I look forward to returning to work to. We operate Canada's 2nd and 8th largest science centers. And maybe you've visited Science North or Dynamic Earth, home of the Big Nickel. Let me know if you have. I love to know where we've had our visitors coming from. So at science centers, we work to connect you with science in your everyday life, to encourage youth to study science, technology, engineering, and math, and also to promote the United Nations Sustainable Development Goals. And space exploration is actually part of our sustainable future. It is also an inspiration to study science and engineering and technology and math and all of that. I was actually motivated to get my PhD and to become a scientist because it maybe brought me one step closer to actually going to Mars. So I hope you share these goals for sustainable development. And I also hope you share a love of space exploration. Now, I will admit, and I think most of the people here know this, that telescopes really do make the best spaceships. And most of our space exploration we do from right here, from Spaceship Earth, right? We're already in space and we are doing so much exploration from Earth. But there are questions about the sun, planets, moons, the origins of life that we might be able to answer if we send humans out to find them. So I believe this is true. I believe we do need to convert the high technology from weaponry to livingry. And that's why I studied biological life support systems. Also, I wanted to be the one running a greenhouse on Mars. I would have settled for the moon. I actually followed my dream, and I became an astronaut candidate with the Canadian Space Agency in 2017. And because of that, I got to know Josh and Jenny, who were actually selected as Canadian astronauts that year. They were both in the group that I was with going through assessments, and Jenny and I were actually buddies for those 4 days. They are wonderful people, and I'm really excited to share their experiences as astronauts. And you know what? They might actually get to go to the moon. But of course, they're not going to go alone. This is going to be an international effort, and they will be going with astronauts from maybe Australia, Italy, Japan, Luxembourg, the United Arab Emirates, the United Kingdom. All of these countries have joined the Artemis Accord. And of course, the United States of America is really leading this charge right now. This is a photo of the NASA astronaut class from 2017. So they are part of the Artemis generation. And if you weren't part of the Apollo generation, then so are you. We're all going to get to share this experience of living and working on the moon. And if you're a kid now, you could go to Mars when you grow up. It's possible. And here's the plan. So it's called the Artemis program. So as you know, most of us know, but I'll refresh, between 1969 and 1972, the United States had the Apollo program. Artemis is the twin sister of Apollo, and she's the goddess of the moon in Greek mythology. Now, she personifies our path to the moon. And it's kind of neat that she's a goddess, because the plan is to return not only men, but women and people of color to the moon. And we plan to have the first people back on the moon by 2024. So that's just 3 years away. So why are we going to the moon? I talked about it a little bit before, but part of it, we want to study planetary processes. We want to look at records of the ancient sun. We want to learn fundamental science, understand volatile cycles, so like especially water, the impact history of the Earth-Moon system, and of course, it's a platform to study the universe. We are going to do some amazing astronomy from the moon. So in this image, you can see kind of in the forefront, there is some blue, and that's representing ice that is on the moon that allows us to live there and explore. And you can see a crater there, that Shackleton crater. So the science objectives are related to just being able to work and live on the moon, but also to preparing ourselves to go further. So we definitely we're going to be learning how to do field geology with significant mobility. So being able to, have rovers and drive around. We'll be collecting samples, returning samples, and we're really going to develop our ability to access regions with really cold temperatures. And of course, we want to install surface instrumentation. So it's not 100% decided yet, but as Jim mentioned, astronauts are going to be sent to the south pole of the moon, and one of the landing sites that is under consideration is Shackleton Crater. So this is Shackleton Crater on the south pole of the moon. This is a visualization. On the right side of the image, that's the sort of the near Earth side of the moon. And on the left side of the image, you're seeing a false color representation of elevation. So blue is much lower and red is much higher. This is a pretty big crater. It's actually 21 kilometers wide and 4 kilometers deep. So it's about 3 times the size of, 3 times wider than the Grand Canyon and 3 times deeper than the Grand Canyon. And one of the neat things about this crater being right on the South Pole is how it's lit. So I have a little video here, and I want you to watch the play of light on Shackleton Crater. Shackleton Crater is that really, really round one right in the center. So you are traveling through a full month here. And notice the rim of the crater. See how lit it is and how the floor of the crater remains in shadow. So what that means is that the ice in the bottom of that crater, if there's water ice there, we think there is, it's there because it's not getting volatilized, it's not getting exposed to sunlight. So on the moon, you need to have a place with dark shadow, deep shadow to preserve water ice. The rim being lit is really exciting because we're going to use solar power on the moon. So this is a great place for astronauts to live and work because they have access to water and they have access to power. And so they can continue their operations. Now, another thing astronauts are going to need to work and live on the moon is really good spacesuits. What you're seeing here, they're actually called Exploration Extravehicular Mobility Units, or XEMUs. And they're spacesuits, but they're also tools, they're life support systems, they're everything they need to be up there, and they allow for bending and moving in ways that our current spacesuits that we use for spacewalks at the International Space Station don't allow us to do. Now, these suits have been built, they're getting tested. I've seen videos of astronauts in them, and we're going to be testing these suits on the International Space Station in 2023. So the XEMUs are a big part of this mission, a big part of the plan. Of course, we're also going to need a rocket, right? Need a rocket to get to the moon. So the rocket we're using is called the Space Launch System, or SLS. You'll hear it referred to. It is really the only exploration class vehicle capable of sending humans to deep space, along with the large systems necessary for them to live and work in space. So it has the power and capacity to lift large and complex payloads. And that reduces the number of launches needed to get the hardware and the people into space. So this is a pretty big rocket. I don't know if you've seen the Statue of Liberty, you've probably at least seen it in films. It's a bit bigger than that. In this side, you can see a little outline of a human and a giraffe for reference as well. But this is a very big rocket. So yeah, we can talk more about it later if you want. Here it is at the B2 test stand. Another component of this Artemis program is Orion. So Orion is a capsule that will be taking astronauts to the moon, returning them. And we can see it here atop of a transporter. And it's in its shipping container. And this is at the NASA Kennedy Space Center. Now, I know it doesn't look like it's very big. It's been specially designed and built to take astronauts to the moon and even beyond. You can see this is the crew module here. So it's capable of transporting 4 crew members into deep space and to provide habitat throughout the launch and landing and recovery. So this capsule, I know it looks tight, but it is actually designed to accommodate 99% of the human population. So it's larger than every other capsule that's been built like this. And it can accommodate astronauts as short as 4 feet 10 inches or as tall as 6 foot 5 inches, which is really a bigger range than we've been able to do before. And it actually provides about 30% more cubic volume of space than the Apollo capsule did. So looks tight, but it's more comfortable than it used to be. So right now, NASA is transforming the Kennedy Space Center into the next generation multi-user spaceport that will be capable of sending humans on multiple missions into deep space, to the moon and beyond. I just love the word spaceport. Here's the launcher being rolled out, and they'll be recovering Orion at sea. So they're also practicing and preparing for that recovery at sea. And the final sort of step is, of course, that landing right on the moon. And so they have a human landing system for that. It's a new and an innovative system. So just breaking it down, there's going to be Artemis 1. So Artemis 1 is an uncrewed test flight of the Orion spacecraft. And it will be sort of like that first test. Artemis 2 will be the first ever crewed test flight of the Orion spacecraft, and it's scheduled to launch on the SLS rocket in 2023. So here, astronauts are actually going to travel further into space than they've ever traveled before, and they're going to go out and around the moon and come back. And this mission is set up to be flexible to like accommodate the science objectives. So it might be as long as 21 days. They're not going to land on the moon, they're just going to fly out and come back. Finally, Artemis 3, scheduled for 2024, just 3 years from now, is the mission that will land the first woman and the next man on the moon. So this is going to be a culmination of really rigorous testing. A crew of 4 astronauts will be traveling to the moon, and they will be landing on the South Pole, but the exact location isn't completely determined yet. Then they'll be collecting samples and studying the moon. So building on this amazing legacy that we have with the International Space Station of international cooperation and collaboration, there is also a plan to build the Gateway. So this would be like a small space station that is in orbit around the moon. And you can see the crew landing module there. You can see Orion stuck on, that sort of cone-shaped Orion with the solar panels. And so this really acts as sort of a base for exploration of the moon. And it's kind of neat because you can sort of be over a location that you want to explore and touch down and explore and then head back up. So you're not limited by, you know, just being able to explore a certain perimeter around a fixed moon base on the ground. So pretty neat mission design, and something that we've prepared to do by participating in the International Space Station. And another important component is Canadarm3. So this is a small robotic system. Canadarm3 is building on Canadarm1, which was on the shuttle, and Canadarm2, which is currently on the International Space Station. And this is Canada's contribution to the Artemis program, along with a program for innovative Canadian science and technology designed for the moon. So we have a cool innovation program going on, but the big hardware piece that we're contributing is Canadarm3. And in return for contributing Canadarm3, we get to send 2 astronauts to the moon. And a Canadian Space Agency astronaut will be part of Artemis 2. So that's coming up soon. And you know, it's kind of awesome. Canada actually has like a really good reputation internationally for space robotics. So, and we're pretty proud of it. Like maybe you've noticed that Canadarm is on our $5 bill. And you can also see Dexter there, another space robot, and of course our astronauts, which are also one of our contributions to the international effort of space exploration. So Gateway is, you know, it's at the moon. It's nearly 400,000 kilometers away from planet Earth, and it represents a crucial stepping stone in humanity's quest to travel onwards to Mars. In the 2030s, Orion will be taking astronauts from the moon to Mars. So this is our next destination in the solar system. And landing humans on Mars may actually be our next mission after the sample return planned for the samples that Perseverance is collecting on Mars right now. So this may be the evolution of a Martian. Now, this picture was taken of Earth in the Mars night sky as seen by NASA's Curiosity rover on January 31st, 2014, about 80 minutes after local sunset. Really is a pale blue dot. And I invite you to imagine actually looking back on Earth through a telescope. Be kind of cool. Okay, thank you. Merci, miigwech. I am definitely happy to take questions. I know I kind of like zoomed right through and didn't give a lot of pauses for questions. So I will stop sharing now, and we have about 10 minutes to just have a chat. I'd love to hear from you.
There was an earlier question about why is it that we tend to use Greek mythology names for space missions?
You know, I don't know. We use the Roman gods for the planets. And so maybe we just didn't want to leave the Greek gods out. And I mean, now we want to use Apollo because of the link. Well, sorry, we want to use Artemis because of the link to Apollo, right? It's just a very nice follow on. But yeah, there's Juno too, right?
We have kind of a question from Michael Falcone. It's relating to how will we, in this new mission to the moon, drive off the conspiracy theorists, the man was never on the moon type people?
Well, I don't really think we need to worry about them, do we?
Is there a big outreach component included in the planning of this mission? How video and imagery is going to make it back to Earth? Oh,
yes, there absolutely must be. And I know I kind of forgot to call it out that this presentation I just gave was an adaptation of Patricia's presentation that she provided me, and she is on the communications team for Artemis. So they are definitely working to get the word out there, to get some cool imagery out there, really help people imagine this and to get them excited about it. So yeah, I don't know all the details of the plan, but I know that's definitely a big component of it.
Excellent. We have a question from Stephen McIntyre. How many countries are involved in the Artemis project?
So right now, I know I kind of listed them off. I didn't count them up, but we have, I can just double check here. Oops, I have it in the note. If I can get to it. I saw that question about Neil Armstrong too. And I get that a lot. Is there like a debate about whether it was Neil Armstrong or Buzz Aldrin? Can someone else on the panel weigh in on this? Will I count countries?
I'm not aware of such a debate.
No?
Yeah, I thought it was pretty clear.
Okay. So yes, Neil Armstrong. So yeah, we have Australia, Italy, Japan, Luxembourg, the United Arab Emirates, the United Kingdom, the United States, and Canada. So we're up to 8 countries who have joined the Accord, and really hoping for more to join because it's an incredible opportunity for international cooperation and really, you know, understanding each other as countries and learning how to work together. You know, if we can get along in space, maybe we can get along on Earth.
We have a question from Martha Farkas. Are there any rules in place to limit future space junk around the moon?
Ooh, this is a really important question because yeah, we have, and I think one of the panelists earlier was talking about like actually how many pieces of space junk, well, how many satellites we have up there and how many, there's a lot of satellites and then space junk on top of that. And it is a problem. And I actually just heard a CBC interview and there was a scientist talking about how it's kind of the Wild West still, like there aren't really a lot of rules in place. There are, there's etiquette and like good practices, like you are supposed to decommission your satellites and make sure they burn up in the atmosphere. But we know that there are accidents, like with China's rocket. So this is definitely something that people are working on and engaging with, but it's sort of one of those areas that we need to be vigilant and to keep working on.
Jim, can I ask an oral question?
Sure, go ahead, Simon.
Olaf, what linkage, if any, is there, given that Artemis eventually will look towards Mars? Is there any cooperative linkage with Elon Musk?
Yes, actually. SpaceX has been given one of the contracts. I should know which contract, but I'm not remembering it right now. I think it might be for the moon lander, but not completely sure. But yes, SpaceX is already involved. Has already been given a contract. One of the contracts.
That contract has been challenged.
I'm not sure.
Yeah, it's been challenged, so it's actually in abeyance right now. Yeah.
Oh, okay.
But I know that Musk says a lot, but he talks about getting to Mars in the next few years, not the next decade or so.
Yeah, it's true. Yeah, it's funny. I have mixed feelings about. I was watching interviews and I learned that Elon Musk's initial dream was to build a greenhouse on Mars, and I was like, oh my goodness, I have that in common with him. But yeah, I don't know. You know, when I was in school doing my master's degree at the International Space University, there were actually like two camps, and one was like with sort of Robert Zubrin, Mars Direct, let's just go to Mars. And there was another camp that was like, well, let's go back to the moon, as we're planning to do, and test out all our stuff. Because it takes 3 hours to get astronauts back from the International Space Station. It takes 3 days to get them back from the moon. And it's about 9 months to get them back from Mars. So we definitely, by the time we're on Mars, we want to be very sure of our equipment and our procedures and how we're doing things. And so it does make sense to sort of practice on the moon and to give ourselves time to get good at it. But, you know, technologically, like if we had the will, we could go to Mars sooner. I think that's true.
I had another question for myself. The Artemis mission, is it planning to be continuous habitation, or is it just periodically visiting from an orbiting platform?
I think periodically visiting. So I found one that in Patricia's presentation, she had notes that they would probably be doing like a couple missions a year and then just being on the surface for about 6.5 days for each of those missions.
Okay, so they're not talking yet about possible permanent living on the moon.
Not in what I read, but again, like this isn't like my super subject area, but I have, we are actually inviting a speaker from the Artemis program, like one of the scientists or engineers, to actually join us for a Blue Coat talk at Science North. So they would, if you keep an eye out for that, they can answer like the nitty gritty technical questions for sure. Hopefully that'll happen in June or July.
Great. I have a question here from Monica Tadra. I don't know if you or maybe Simon could answer it. Is the moon only made out of rocks or something else?
Well, the moon is actually, we think it's a chunk of the Earth. So there was proto-Earth, and then there was another planet, which they're called Theia, and they impacted and kind of glommed together, but like a chunk broke off and went into orbit, and that became the moon. So the moon is made of the same stuff as Earth, but it's different because it hasn't had life, right? So all the organic matter we have on Earth, the soil, you know, that sort of stuff hasn't developed on the moon. So the moon is kind of rock and it's dust. So we call the surface material regolith. But yeah, and then yeah, jump in if there is someone else on the panel who wants to add in, that'd be great.
No, the only other thing one would add, Olaf, you've already actually alluded to, which is the possibility of water ice.
Yes.
Otherwise, we're looking at rocks.
Yes.
Which is great from a geological perspective.
And of course, that ice would have come from comets and asteroids impacting the moon, making all those beautiful craters that we see when we look up at it. If I haven't had a chance to answer all the questions, I do have I do Saturday evening star parties at 7 p.m. With Science North. So we're on YouTube and Facebook. And if you'd like to join in this evening, I can answer more questions. And I'm going to look into that, you know, how long people will be on the surface and whether they're going to try to do continuous habitation of the gateway the way they have been doing with the International Space Station, because I have a feeling they might be.
Great. Well, thank you very much, Olaf. That was a fascinating presentation on the near future going back to the moon. It's quite soon. I'll be surprised if it actually stays on schedule, but I guess we'll see.
We've definitely had some hiccups, some bumps in the road along the way. But
yes.
Thank you so much for having me, and enjoy the rest of the program, everyone. Bye for now.
Thank you. All right. While we transition over to our next presenter, which will be Simon Handmer, talking to us about what's new in the news in the solar system, I'd just like to remind everybody of a few pointers about the Zoom interface and the Zoom webinar. So you might find from time to time people who aren't really behaving themselves, posting things to the chat. And so if you find people putting links in the chat, please just ignore them. We will not be putting anything in the chat. If we have information that we want to share with you, it'll be on the shared screen. So I would just ignore anything you see in the chat box asking you to follow a link. Also, because it's a little bit, it can get busy monitoring both the chat window and the question and answer window. Please try to put all your questions into the question and answer window in the Zoom interface. It's a lot easier for us to monitor that and not miss anything. And also, there's a Zoom feature to raise your hand. We won't be paying attention to that. We'll just be mostly focusing on the Q&A window. So with
Jim, it's Chris. We've actually disabled raising hands. It cannot be done.
Oh, you have. Okay, great. Well, thank you, Chris. So without further ado, I give you Simon Handmer.
So I'm hoping you can see my title page.
Yes, we can.
Good.
We can see it. Yeah.
So, what's new and news in the solar system this year? Well, let's just start with the realization that from the point of view of solar system science, we are literally in the not so much the golden age, but certainly the dawn of the golden age, and the very proactive dawn. You've got the national and international space agencies falling over each other to get out to the solar system. Just yesterday, I read the Chinese have landed a new rover on Mars. They haven't actually dropped it from the lander itself. They're doing all kinds of technical checks, but everybody wants to go to a planet. I know the Indians are out there. Even the Gulf states are sending a probe into space, either to orbit planets and other solar system objects, or to actually land. So it's a wonderful time. And the other thing is that almost all of them are trying to advertise the science that they are doing, probably to justify to their governments that the investment by the governments is worthwhile. And so they're putting all of their information on the web. Now, they're not just putting numbers and chemistry and complicated formulae. They're also putting images, which are pre-digested, which means that the likes of us, amateur astronomers, we can go onto their websites and we can actually observe these things within literally hours or days of these images having been taken. And sometimes they're so keen for us to know about it that they will actually proactively tell us through the internet that things are available to be seen. So what I want to do here is to have a look at where are we in 2021 with respect to solar system science. What's new, what's news, what are the questions that scientists who are working on this are asking themselves today? Not 10 years ago, 15 years ago, maybe not even 5 years ago. What are they talking about today? So just a reminder, you've already seen this slide here earlier today. This is a slide where the sun is to our left, the various planets and objects are out towards the center and the right. The distances between the various planets are not to scale, but the sizes are. And of course, as everybody likes to tell us, we are kind of small potatoes in this. But then so are some of the other most interesting planets. Mercury is literally just a speck. Venus is about the same size as Earth. Mars is much smaller. And then these are the big guys out further out. We will mention Pluto. I know it's been relegated to a dwarf planet, but we will actually mention what people are thinking about it these days. So I'm going to start in the interior. And I'm not going to take you through a history or a context or the scientific setting of a given planet. I just want to highlight what are the kinds of things that are actually making scientists scratch their heads today in 2021 on a given planet. So it's going to be a bit of a scrapbook, which is fine. That's done intentionally. So let's look at Mercury. Remember, Mercury is bone dry. It has no atmosphere. It's like the moon. You wouldn't not want to go and live there. You'd have to take everything, including the kitchen sink, if you did. So when scientists saw this stuff here, they scratched their heads. They're still scratching their heads. And they said, what on earth is going on here? Now, these are false colors. But the blue is something really interesting. We don't know what it is. The holes that you see here are real. And if you look at the distribution of the holes and the blue stuff, it looks like the holes are forming where the blue stuff is, I use the word evaporating, but the technical term is sublimating. In other words, something solid is turning just like that into a gas, not going into a liquid, but into a gas. And the thing is nobody expected Mercury to have something volatile. What's the kind of thing that you know from your own back and front yards at the end of the winter that sublimates? Water ice, the end of the winter. And you hope that that ice is going to simply disappear as water vapor without turning into water itself and then backing up into your basement or coming in through your roof. Well, this is what the kind of thing they're seeing. Now, let me just take you to the next slide here, which gives you it's the same stuff. These are the holes. There are the same textures. And here's an example of some big holes and the same color. But the reason I put this slide in is it shows you scale. That's 5 kilometers. That's 25 kilometers. So this is a really large patch. This is as big as half of Ottawa. Of whatever it is that is sublimating. And this is a detail, if you like. This is what this would look like if you went in close. Nobody knows what it is. Oh, there are lots of theories, and I won't bore you with those because let's wait and see which theories actually stand up. But there are all kinds of things that could be highly volatile on the moon, but there are all kinds of reasons why each one of the suggestions may not really be robust as yet. So let's move on to Venus. Well, you've probably heard about this one. This is the head scratcher this year. You've seen it all through the general media, the newspapers, the radio, the CBC, for crying out loud. Life on Venus, somebody says. And what all this is to do with is that a very simple molecule, illustrated here, we'll look at the molecule in a minute, called phosphine. Some thought that they had managed to discover this by looking at the clouds which surround Venus. We can't see the surface of Venus because it's got this extremely thick, very, very dense atmosphere of carbon dioxide, sulfur, and so some thought maybe phosphine. And the reason phosphine gets people excited is that phosphine, as far as we know, is only generated by life. So here's an artist's impression of phosphine molecules. This is what a phosphine molecule is. It's phosphorus and 3 atoms of hydrogen hanging around it. I won't get into the details, but phosphorus is very important in life. It actually is the mechanism whereby in your body, when you eat food and drink fluids, in order to convert all that stuff into energy, phosphorus plays an extremely important role. And so people got very excited and wondered whether this meant that up in the upper reaches of the Venusian atmosphere, maybe there were bacteria, for example, which might be metabolizing and generating this phosphine. Well, it turns out that when other people started looking at the evidence, they said, look, really, we're not convinced. It could be all kinds of other things, and maybe you're not using the right method. So I don't think one should get excited about this. I don't think you should think that, oh, wow, they've managed to find life on Venus before they found evidence for life on Mars. And of course, on Mars, they're looking for fossil life. This proposal was maybe life actually in the clouds of Venus today. I don't think one should take this too seriously and should not get excited about it. Nevertheless, Venus is becoming more and more a point of interest. People working on Venus have felt very much the poor relations, especially with respect to NASA. NASA's been very much focused on Mars and focusing now more and more on the moon as a stepping stone out to Mars. Elon Musk, as we've talked about, wants to go to Mars. Everybody wants to talk about Mars. The Chinese have just landed on Mars, and poor Venus. The last time anybody actually went to Venus and did not land, some have landed, let's not worry about those. The last time NASA basically mapped the surface of Venus, they did so using radar from an orbiting satellite. And that was back in 1990 through to 1994. So most of the data mapping the surface of Mars, not the clouds, but down on the surface, the rocky surface, is over 30 years old. And it was relatively old technology. And so a lot of people have said, look, you know, we should really go back and have another look. We've got much better radar than we had back then, much better resolution. And they've said, well, maybe what we should do is put together a multifaceted experiment where, yeah, we have some mapping of the surface using radar, but let's actually spend a lot of time understanding the atmosphere. And the general justification there has been, well, we're talking climate change on Earth. Clearly, there was major climate change on Venus. The surface of Venus, by the way, the temperature is 450 degrees centigrade, which is hot enough to melt lead. And the reason it's that hot is because of the CO2 in the atmosphere. Now, the CO2 in the atmosphere on Earth is something like 0.0045%, whereas on Venus, it's much closer to 99%. But the thing is that we really would like to understand the evolution of the atmosphere of Venus and all kinds of other things too. The reason partly is because Venus is Earth's twin. So right now, and this is the message of this slide, there are actually a number of teams putting forward a number of proposals for new missions to Venus. And it sounds as though at least NASA might be interested in entertaining the idea of a return to Venus, at least in orbit. They're talking about the possibility of dropping some kind of robot down onto the Venus surface. It probably won't last more than a few hours because of the temperatures, but you might want to keep your eye on this. Certainly the general media are certainly talking a little bit about it. Artemis, I'm so glad that Olaf actually told you all about Artemis, because now I can actually pass on this. I have the same slide that she had, but the reason that I had this slide is this guy. I'm trying to work out as a geologist. I was a professional geologist for 40 years before I retired. I'm trying to work out what this guy is doing with this hammer, because that part looks like a hammer, but what's this thing on the bottom of it? I'm wondering if maybe I've got it wrong and that this is not a geologist at all. And it's another one of these chemists who are trying to take some kind of compositional analysis of this rock. But the reason I've got the slide in there is, what is the science question that I think, and many other geologists think, and planetary scientists think, we should be asking about the moon, and why is it that the Artemis mission is the perfect opportunity to address the issue. Jim has showed us pictures of the moon with large and small craters, and that there are terrains with lots of craters, which are old, and there are terrains with much less craters, which are young. And the thing is that the return samples from the Apollo mission were used to try and calibrate the time scale for the entire solar system. If you look at Mars, if you look at Mercury, you can see the same business. You can see terrains with lots of craters and terrains with less craters. And so there are older terrains and younger terrains. And because the samples that were returned from the moon were analyzed in laboratories, people thought they could work out what the time frame was for the old craters on the moon and what the time frame was for the younger craters. Well, it turns out that for the last decade or more, we've been calling this into question. And this is extremely important because the way that people try to understand how old features on Mercury or on Mars might be, and even features on the icy moons around the outer planets like Jupiter, Saturn, and what have you, is by calibrating against the analyses they did of the moon samples. Well, it now sounds as though the moon samples were all from the one single event, and that maybe we don't actually understand the time frame of the impacting by asteroids and meteors and what have you into the moon. And so this would be a perfect opportunity through Artemis to actually correct this. And in doing so, we'd then be able to correct the time frame for the entire solar system. So we all know that NASA has gone to Mars, and we know that NASA has dropped the Perseverance rover into a Jezero crater. And the reason they've done it, the rover is sitting around about here. This is the edge of Jezero crater. And the reason that they got really excited is this shape here. What this looks like is a river, no, sorry, a fossil river, a channel from a river about 4 billion years ago that flowed into a lake which filled a big crater called Jezero crater. And just like any river that flows down to the sea, think of the Mississippi Delta where New Orleans is. So the river slows down, it's carrying sand and gravel, it dumps the sand and gravel and it forms a delta. And they think that this, and I think they're right, this is a delta in Jezero crater. This is an oblique image taken from an orbiting satellite of the delta. And the idea is that the lander is over here, it'll have to work its way around. They actually wanted to land here, but they couldn't. They landed here instead, that's fine. They'll work their way around and then they've got to get up onto the delta. The only issue is that this is what the edge of the delta looks like. Well, you know, if you and I had really good hiking boots and not too much of a backpack and we had some Sherpas carrying all of our gear, we'd still be sort of huffing and puffing trying to get up this slope. So this poor thing here is going to have to get up there somehow or another. I'm sure that they've got all kinds of pathways mapped out. And the idea is that because the delta has to indicate the presence of standing water on the surface, that is where the best environment might be to try and find fossil evidence of fossil life, perhaps billions of years old. So this is where we are right today. This is where on Mars we are right today, and this is why they've gone there. This is still the same story they've been telling us about Mars for the last 20 years. Fine, let's go with it. I still believe personally that these rovers are not really telling us anywhere near as much as the orbiting probes which go around Mars with their cameras which have fantastic resolution which improves every time they send a new probe. I think those orbiting probes are still the ones that are going to be telling us the real science stories. But let's see how Perseverance does. You go out to the gas giants, and that would be essentially Jupiter and Saturn. And the real thing of interest here is Jupiter itself There's the Jovian mission, which is orbiting Jupiter right now. It's really studying Jupiter's atmosphere. Mind you, the difference between Jupiter's atmosphere and its core is difficult to define because the atmosphere is essentially hydrogen, methane, and all kinds of other gases. And the core is those same gases, but compressed so tightly that they become solid, and then you keep pressing them tightly, and they become liquid metal. Yes, I said liquid metal. I don't mean mercury. I mean liquid metal hydrogen. I have no idea how to describe that to you. You'll just have to believe me. This would be, as at size, what this is. This, of course, is Europa, the ice moon. And the interest today in Europa, of course, is the idea that it may contain an internal ocean. So what's being put together right now, today, even this year, people are putting together ideas for actually landing some kind of a probe on the surface of Europa, dropping a drill down. There's various ways of doing it. We're trying to drill down through the ice shell and down into the ocean below, and then go literally looking for life. But this time, maybe even life today. With respect to Saturn, this is the largest moon around Saturn. This is Titan. This is what Titan normally looks like. If you were actually to arrive in a spacecraft, this is what you would see. This is in visible light. But of course, there was the Cassini mission to Saturn, which got there, I think, about 10 years ago. And it kept going, whizzing past Titan. That was done on purpose. And they looked down into Titan with radar, looking through these clouds of methane. And what did they see down there? Well, they saw what looks like rivers and what looks like lakes and seas. These would not be water, these would be hydrocarbons. So although we've been looking at this for the last 10 years, still the question that's being asked is, what exactly is on Titan the equivalent of the water cycle on Earth, where you get rain, you get rivers, you get seas, you get oceans, you get evaporation, and you get rain again, and so on and so on and so on. So the question is, what really is going on with the ethane, methane, hydrocarbon cycle on Titan? And is there any chance that some form of life actually managed to form in that hydrocarbon environment? That is still very much on the table, and they're talking again about sending back a mission to Saturn, but specifically to Titan. The ice giants, that would be Uranus and Neptune. Right now, these really are the poor relations of the solar system. I was looking, I follow on a regular basis all news coming out and science papers coming out on anything to do with the solar system. And to be honest, there really hasn't been much coming out on either of these two. People are still trying to work out why it is that Uranus is on its side. In other words, that's the North Pole, that's the South Pole, and it's almost horizontal. In other words, lying in the same plane as the planet is orbiting. And the moons that go around it are going around in a plane that's perpendicular. People are still trying to work out why that happened, but there's no new observations. And so what they're doing is they're playing essentially with computer modeling. And for Neptune, the computer modeling is essentially relating to the development of the atmosphere. That brings me to the edge of the visible solar system. And here we are at Pluto. Now, okay, Pluto is not a planet. It is not a planet. There is no debate to be had about this. The reason that Pluto is not a planet is that outside of the orbit of the major planets, there is a large disk called the Kuiper disk, and outside of that is a huge spherical cloud called the Oort cloud. And these things are full of things which range from comets to other minor planets. And it turns out that Pluto not only resembles those outer minor planets, but its orbit is not circular, semicircular around the sun, and it does not conform to a plane that's in the same plane as the other planets. So it really is a Kuiper belt object rather than a planet. But when the New Horizons probe zipped past a couple of years ago, and they started taking photographs very, very quickly. An absolutely miraculous experiment of the surface of Pluto. They got the shock of their lives. What they were expecting, Pluto is very small. It's on the scale of our moon. It's a bit bigger, but it's on that kind of scale. And they were expecting it to be old, cold, and dead. In other words, nothing happening. And they got there and they found that there were almost no impact craters. Here's a detail of the surface. Not only that, not only were there almost no impact craters, that might be where. Oh, and if there are almost no impact craters, that means that the surface is renewing itself. So that means it can't be old, cold, and dead. It means that something must be happening to churn the surface up and bring up new stuff onto the surface and take old stuff down and recycle it. And they were finding all of these kinds of patterns, which were telling them that all kinds of active events are occurring on Pluto. And not only that, but they could see this huge area here, which actually is heart-shaped. There we go. And this is a huge sea, if you like, of nitrogen ice. There it is, right there. And it's flanked on the sides by this water ice, which is formed of mountains. These mountains here are kilometers high, 5-6 kilometers high. That's why they know it's water, because it turns out that if it was nitrogen ice is so soft, it would form a flat surface. It would collapse under the weight of all this mass. So they get there and find that there's all of this stuff going on. Look at this, not one single impact crater in there. So what's the head scratcher for Pluto? Why is Pluto still active? That means there's heat inside Pluto, which is allowing all kinds of geological processes to occur. And they're trying desperately to understand what on earth could be keeping Pluto alive. The other head scratcher is this stuff out here. This is the atmosphere. This, by the way, is the reason that the New Horizons probe never got into orbit around Pluto. It went whizzing right by. And that's because they sent it as fast as they could, because they knew that because of the weird orbit that Pluto has, it was getting colder and colder and colder. And the atmosphere that they knew existed was actually freezing out onto the surface of Pluto. In another 5, 10, 15, 20 years, there won't be an atmosphere. It'll all be frost down on the ground here. So they wanted to send it real fast, so it whizzed by. But the thing is, they really want to analyze both the physics and the chemistry of the atmosphere. So currently, the work that's going on is head scratching. How do we generate heat inside Pluto in order to account for the fact that its surface renews itself so quickly that there are no impact craters to speak of? And what on earth is going on? What are the dynamics of the atmosphere? And that, I think, brings me to the end of what is new and news in the solar system. Bottom line, there is so much going on. Every now and again, you do hear about Neptune and Uranus as well, but it's getting rare right now. But Venus, keep your eyes out for all kinds of news about new missions to Venus. Keep your eyes out for what's coming out from the Perseverance rover and new rovers that are being launched and have just landed on Mars. Keep your eyes out for new stuff coming out from the ice moons around the gas giants. And what will they come up with next? It'll be modeling, because there's going to be no new data on Pluto for decades. So you can expect to see lots of new modeling ideas. Modeling is great. Modeling using computers, it gives you ideas, but it doesn't prove anything. It just shows you that things are possible, feasible. You really need to go back with new data to test the models. So that's it from me, and keep your eyes on the solar system.
Great, thank you, Simon. So the remaining 30 minutes up to the supper break, we have opened up to the floor to just general questions. If anybody in the audience has a question on any topic relating to astronomy, now is the time to ask. To kick things off, I have a question here that was emailed to me by Sky, age 13, living in Highlands, BC. And their question is, what does a black hole look like from every angle? Do they all look like the pictures I've seen showing the event horizon, or does it look different than that? Would anybody like to answer that question?
That one's a toughie. I think one of the best ways of answering that is the famous analogy, whereby the idea is that there you are, you're an astronaut and you're floating in space, and you've been caught by the gravitational attraction of the black hole, and you pass through the event horizon. The idea is that somebody outside of the event horizon watching you go in would see you basically disappear, because the event horizon is the limit where light cannot come out. So if you've passed through it, nobody can see you. But apparently, as you go through, you know nothing about it. You don't find out that you've gone through the event horizon until you start feeling more gravity attracting. At that point, things get rather difficult. That's when your feet start moving in towards the singularity in the black hole faster than your head does. And that's where you get stretched. But if you're on the outside, no, I think you see what people have actually drawn in the cartoons.
Well, there's a slight difference. You can't see the event horizon, but you can see all the matter that's falling into the black hole, assuming it's a black hole that has matter falling into it, rather than a black hole that's isolated in space. The matter falling into a black hole doesn't fall in symmetrically. It typically forms what's called an accretion disk. So depending on the angle that you're looking at the black hole, you will see slight differences. You'll see either a ring or a bent ring, or what appears to be a ring and a half. There are a variety of photographs and illustrations showing that on the net. It would be interesting, but I wouldn't get too close.
Great, thank you, Attila.
We do have a representation already of a black hole that was published on the internet not too long ago. The famous picture, which we can't link.
We might be able to share it though. Let me see if I can pull it up quick. You're talking about the image of the black hole of Messier 87?
Probably. Now this would be obviously a representation of the data, right? A visual representation, probably of radio data.
Yeah, it was done as done by the ALMA array, so you're operating in submillimeter. Yep, there it is. But what you're really seeing, as much as anything, has been described as a shadow. You're seeing light warped around it, and nothing in the middle, which is what you'd expect. Or I should say submillimeter radiation. It's still, you can still think of it as light, of course. You're not going to see this naked eye.
The light that you see is from the matter falling into the black hole that gets compressed and accelerated, and it gets so hot that it begins to glow. But because the black hole is bending space and causing light to curve, the accretion disks that we would see would look warped in interesting ways. Which is why, for example, it doesn't look like a uniform circle, probably because we're looking at it at a slight angle.
All right, I have also an answer to an earlier question that I had asked Olaf about continuous habitation of the gateway, the Lunar Gateway facility. And she went and I guess asked her source and found out that it will not be crewed continuously, but it will be inhabited at least once in a year. Canadarm 3 has an AI that will tend the gateway and operate science experiments when the humans are away. That's kind of cool. Kind of creepy too. Astronaut showing up after months of the Canadarm3 being all by itself. It could be a little creepy.
Yeah,
I can't open the door, Dave.
Yeah, exactly. Shades of 2001.
No kidding.
All right, we have a question here from Roger. Where does a black hole lead to? Is it like a circle where things just go through?
You can't really say that where it goes. I mean, there's been all kinds of philosophical discussions about it, but really what's happening is once you get beyond the point where you can get any information, we're coming into an area where the laws of physics that we know don't work anymore. So anything that we can project is 100% conjecture. Whether you want to call that leaving the universe or whatever, I think that's more a philosophical question.
Yeah, Tim's right, but remember that some of the great minds are speculating. Lee Smolin, for example, of the Perimeter Institute, who's no small potatoes, neither he nor the Perimeter. He wrote a book where he suggested that, in fact, universes in the plural evolved in order to create black holes, because he felt that where black holes went was actually into budding new universes. Now, there's no way that I can follow the physics on this whatsoever, but if somebody like Smolin is prepared to speculate at that level, there must be a certain at least underpinning to the discussion. It can't be entirely off the top of his head.
No,
I don't know how he got there.
Actually, I read about that, and surprisingly, this is one of the speculations about the interior of a black hole, which is almost testable. What this guy conjectured is that stuff falling into the black hole forms a new baby universe, and he's guessing that the laws of physics of the baby universe may vary very slightly from the parent universe. And he thinks this is happening over and over again, millions of times, because there are millions of black holes that we know of in our universe, and untold number of other universes also creating black holes. He thinks that just generally speaking, that means that we are likely in a universe which is the descendant of many other universes for many generations. So our universe should be optimized for creating black holes. And what he specifically stated was the 100 or so physical constants, like the fine structure constant, which we don't know why it's the value that it is. He conjectures that if we changed one of those constants, even by a slight amount, it would reduce the density of black hole in our simulated universe. So this is an almost testable speculation about the interior of black holes. But Tim Cole is right. Basically, since we can't get information out of a black hole, there are no truly scientific statements you can make about the interior of a black hole. But it is
not unless we can come up with some kind of theoretical basis for expanding what we think. I mean, one of the weird things you can get with rotating black holes is the theory does allow for the existence of a naked singularity, which kind of gets a whole lot of people's knickers and many twists. But I must admit, I have trouble with the math on that.
Anybody uncomfortable with division by zero would have trouble with the math on that.
Well, yeah, no, but the whole question of the flattened, the inside and outside of the ergosphere touching at the rotational poles. I am told it works, but I don't know enough topology. Or enough differential geometry.
It's been concluded that general relativity simply cannot describe the naked singularity properly, because the naked singularity would have dimensions small enough to be dominated by quantum mechanical effects. And currently there's no integration between the theory of quantum fields and general relativity.
No, they're definitely on a timeout.
Yeah, so basically they know that we have no theory that can properly describe what happens at the so-called very center of a black hole.
Yep. That's why I love the cartoon showing the breakdown of physicists in the region of the singularity.
That's a good segue. I have a follow-up question from Sky. They're asking, if I wanted to study black holes, what would I need to do for school, and what profession could I do?
Well, let me tell you, Sky, there is a course either at edX or Coursera. I was trying to find it while you asked that question. It's free. You can audit the course. You will need some high school algebra to do the course. But you could, if it's free, you could always check that course out as a good starter. And obviously, you'll need a lot of math. You'll need to do physics as you go through high school. And eventually you'd be studying astronomy. All I could tell you is keep your nose in your books, do a lot of homework, and that's what will get you started.
Yep.
But prepare to understand math and avoid math phobia. Math phobia puts so many people off. I do an introductory astronomy course, which has very little math involved. And when I show just a picture of how to do a parallax, just a triangle, I constantly get complaints about I can't handle all the math. So math isn't this horrible, terrible bugaboo, but it tends to be taught badly. So avoid the phobia.
Tim, I agree. But one of the reasons it tends to be taught horribly is because it tends to be taught in a vacuum. I mean, to be honest, when I was learning math, I really didn't care how fast the car went between New York and Chicago.
You too, huh?
But if you decided, as Sky has, that, hey, I think I would like to understand black holes or some such thing. If you now have a reason to understand the math, then the math becomes more tangible. There's a rationale, a reason, and it's worth now knuckling down to try and work out how it works.
I know for me, it didn't really click until third year university, when it finally all started to come together. Before that, it was just, stuff. And why the hell am I doing this stuff?
But I had to have an answer to that question. Why am I doing it?
Yeah.
And Sky seems to already have an answer to that question, which is very good.
How can one demonstrate the gravitational pull between two objects? Interestingly enough, I don't know if this is a good demonstration, but back in first year physics, we had to do a problem, which was to calculate the gravitational attraction between two supertankers parked at a pier. And when we came up with the number, it was in the hundreds, maybe even the thousands of tons. And it's not anything you're inclined to imagine. Now, unfortunately, that's not much of a classroom demo. The problem is the force is so incredibly small.
Yeah, the only thing I can think of is maybe a pendulum experiment.
Yeah.
Where the equations of gravitational attraction can be transformed into figuring out the period of the pendulum. So that's something that you can try.
Yeah, unfortunately, we can't change the gravity.
There are a bunch of science museums in London, England, and I'm pretty sure they probably have Cavendish's original laboratory apparatus. He built what's called a torsion balance. It was a bar held by a very thin piece of quartz fiber with two balls in it, and he put those movable two balls next to two large fixed balls. This was small enough to put it in a laboratory. And knowing what the weights of the four balls was, he predicted what the forces should be, and he was actually able to measure the force based on the torsion on the glass fiber.
Yeah, and get a
high school demonstration, but the apparatus, I suspect, still exists.
Probably does, though it had to be operated in a near vacuum. I know it's been replicated a whole bunch of times, but again, it's tiny. It's a tough thing to demonstrate.
Folks, Cicely has a question here, which is very interesting. She's talking about a classroom situation. And how can one demonstrate the gravitational pull between two objects in a classroom full of non-algebraic children?
Yeah.
Now this is a very, very, very good question.
It is. I'm just trying to come up with a good one.
I was going to say, if we are looking to interest the next generation in science, maybe astronomy, maybe not, we need to have an answer to that question.
We do.
The simplest demonstration would be to drop a pencil, but it's not very convincing. That is a demonstration of the gravitational attraction between two objects.
Chuck has a suggestion.
I'd suggest you just use the ball on a sheet, and you're getting a little bit of a leapfrog on relativity.
I've never liked the ball on a sheet. I've never liked the ball on a sheet.
Children would understand that a lot better than anything you tell them. If we sit there and speak to them a wall of text or
oh yeah,
speak to them paragraphs, it's going to go over their head. If you give them a demonstration that they can interact with, let a child flick a marble with his thumb, they're going to remember that a lot more. In our earlier years, we remember actions more than a lot more than we'd ever remember words.
Yep. Yeah.
Actions, pictures, drawings. Yeah.
Yeah. Your earliest memories are when you were doing something. So
I agree. Entertainment may be more important than factual demonstration. And in particular, you wouldn't want to show them the actual mathematics, because have you actually ever looked in detail in the mathematics of general relativity?
Yeah, I've got 2 books in my bookshelf.
I used to like mathematics until it became tensor.
No, tensor is enough to make well, that's how come we're bald.
I heard you guys talking about hands-on demos and the fabric of space-time and gravity demo, and I just wanted to share this one quickly. It works really well if you just have an embroidery hoop and some fabric, and then you can show that bending of space-time. Works pretty well.
Perfect. Thank you. Very practical. We have a question here, still on the black hole topic, from Monica. Is the black hole connected to gravity? So I'm assuming that's more of a general question about what is a black hole, basically.
It basically is gravity. Gravity overwhelming everything else. Sorry, I have another computer dying behind me. Yeah, it's basically gravity overwhelming everything else, really. It's a testimony to gravity. I don't know how much that answers the question.
I think the way to answer the question is to point out how we think a black hole actually forms, with the collapse of a really, really large star as its heat engine internally, which is what stops it from collapsing. The star tries to collapse because it's a huge mass. Just like when we jump up and we fall down again, we're being pulled down by gravity. So the mass of the star is being pulled in towards its center by its own mass, but the star is hot inside. If you turn off the heat engine, which is what happens at the end of life of a star, then all that mass then starts to collapse under its own gravity. If it's massive enough, then for reasons which we won't go into here, it will end up as this black hole. But it ended up there because it went from something which was balanced between gravity and expansion due to heat. It went to something where gravity took over.
And had no opposition at all.
Exactly. So gravity then becomes everything that actually generates the black hole.
You can have some intermediate steps. I mean, you might have a white, white dwarf, neutron star, whatever the heck else is below that.
That's why I said we'd pass on the intermediate steps.
Oh, the intermediate steps are fascinating.
Yeah, I know, but we may have a few 10-year-olds listening to us.
Yeah, true.
Next time,
white dwarfs and neutron stars are far more fun than black holes.
I know they are. I know they are. I mean, hell, neutron stars are even geological.
Richard McDonald is the one guy I know of who's an amateur astronomer and also has a PhD in astrophysics. I'd just like to point out to the people asking questions is we're amateurs. We're basically guessing, repeating what we've read in Wikipedia and textbooks and things. But there are a few people around who have actually studied this material. So you should consider our answers to be unofficial.
Yes.
Or wild guesses.
Well, we're not published, but some of us have studied a little bit.
Well, some of us are published.
Okay, so we have about 10 more minutes until the supper break. Are there any more questions from our audience?
Oh, come on, we don't fight.
Well, not too
much. Not much.
I'm a bit surprised there aren't more questions about telescopes and astronomy.
Yeah, come on. You can at least make us sweat.
I can certainly pull out a discussion topic. Actually, Michael Wolfson had a good topic. What is better, a small aperture or large aperture? Go.
Oh.
Both.
When I was a young man, a large aperture. Now that I'm an old crock, a small aperture.
So last Astronomy Day, I gave a talk on different kinds of telescopes, and I tried to argue there's a place for both large aperture and small aperture telescopes. There are fundamental differences between them. There are things that a small telescope can do that a big one can't, which isn't obvious. The most basic thing is small telescopes typically have a much wider field of view, and there are some objects in the sky that you can't really get a good look at because you're only seeing a tiny portion of them in a large telescope. The video for that is on the RASC YouTube channel called, I think, Second Look at Telescopes.
Yeah, there's no question a rich field telescope can do wonderful things. Classic example I give for people is look at the Pleiades through even a moderate telescope, and it's dull. Look at it through a pair of binoculars, and it's magnificent.
I have a 25-inch telescope, which is bordering crazy, and when I look at the Pleiades or the double cluster, I don't see anything because it just looks like an ordinary star field.
It's a star. Yep.
Small portion of it. The best view I've had of the Pleiades and of the double cluster has been through a 70 millimeter. That's about 2 3/4 inches telescope. So I have a large aperture telescope, and I also have a large field telescope. Turns out the large field telescope is really small.
Yeah, it has to be. And but seriously, I was being a little flippant in talking about the weight. One big thing, and it was said earlier, that the best telescope is the one you use. So if you've got something that you can no longer move, it's not helping you.
Just like to add that myself, even though like I'm a very visual type observer, like I like the Dobsonian, I like the simplicity of it. But I do have an appreciation when I see people with the video astronomy, how they can turn a very small telescope, like a refractor or something very, very compact. And with those high sensitive video cameras, they can make it appear as a much, much bigger aperture, like 4 or 5 times the equivalent aperture because of what the sensitivity of the camera is able to do. So that's pretty amazing what we can do with technology.
Yeah.
This one here is 4.5 inches Newtonian. So it was $200 about 15 years ago. It's good for my purposes.
Folks, Kelly, 12 years old, is asking a question. She's asking how telescopes work.
Well, there's a couple of different ways they can work. There's two basic styles. One is if you use a funny shaped mirror, which is sort of like the ones you see in stores that let you see around the corners, except they go backwards. And the other way to do it is basically hold 2 lenses in front of yourself. Hold 2 magnifying glasses in a line, and you'll have a really, really cruddy telescope. It won't work very well, but that's basically the principle of a telescope. You have one lens that pulls in light and another lens that magnifies the image for you, and that's the eyepiece. The telescopes work a bit like the shaving mirrors. They have a bit of a curve in them, and because of that funky looking curve, it makes it so that you can see all the pimples on your face in exhausting clarity.
I think another way to say it is that the basic idea of the optics of a telescope is the telescope will collect more light than your eyes, so you'll be able to see fainter things. It also makes the apparent size of the object bigger, in other words, magnification, so you can see things that look smaller.
Yeah.
And the trickery of how this is done with lenses and mirrors is actually mathematically quite complicated.
Oh yeah, of course it is, but.
Or another way of looking at it is what telescopes do is they convert money into swear words. Because if you have a good telescope looking at a really interesting objects, I've noticed that people will spontaneously swear or say, oh, wow, oh my God. Or,
yep.
Like if you Google the expletive scale of astronomical observation, this is a web page I wrote years ago where I recorded things people have actually said when they've looked through telescopes.
Yeah, it's intriguing.
Scale of more and more outrageous swear words.
Yeah, there's definitely been a few of those.
There's been a few of those for sure. Every time I've climbed up that ladder to look through a telescope.
Well, I find I can't do it without my supplemental oxygen, but anyway.
Well, this evening will be interesting because whether we can see live or not, and looking out the window, I doubt we can.
No, I don't think so.
But we definitely have a good collection, a good selection of things which we have seen through a variety of telescopes. I'm going to be focusing on things I can see through a 2-inch refractor, And my goodness, that field of view is big. And others will be using different telescopes of different sizes and what have you. So people will get a chance to see different things that different telescopes can see.
Yeah. I find I get a lot of use out of my 4-inch simply because it's small. I can put it in my trunk. I can set it up and take it down in minutes. And okay, I can't get the magnification with it. You know, I can't see Mars in great detail with it, but there's still an enormous amount that can be seen, and you use it. And that's the big thing. The telescope you don't use is no value at all. And don't forget binoculars, yes. Though don't forget, with binoculars, you've also got to hold the silly thing steady. And this is where a lawn chair comes, or as I've suggested to people, get an old sponge mop, rip the sponge off and get a bungee cord. Hold the binocular steady. You know, you don't need a lot of money. The beautiful part with binoculars is if you suddenly, you know, if you really decide that you're not into it, if you're not into the astronomy thing, I don't know how that could happen. You know, you can at least use it for bird watching or sports or something else. So, you know, you haven't lost the investment. And every astronomer I know of has at least one pair of binoculars.
Actually, Tim, you just touched on an extremely important point with respect to telescopes. You never actually lose the investment because there are stores which will actually allow you to trade in and trade up.
Yeah,
so
true.
You can almost always find some residual value to a telescope you started with. You get ambitious, you think, well, I'm going to go to the next step, but you don't just simply put your telescope out as garbage. There are people who are starting after you who would love to buy your telescope secondhand, and there are shops in town who would love to actually broker it for you because they want you, of course, to buy a new one from them.
Of course,
fine.
yeah.
It's exactly
as long as you've got something decent to begin with, and I mean, if you bought some big box piece of garbage.
Yeah, as long as you get something that doesn't wobble too much.
Yeah, well, the big box piece of garbage, that's the problem with it, is nobody wants it.
People new to astronomy thinking of buying their first telescope, it is true that a used telescope will cost less money, but I believe it's much harder to do a good job of buying a used telescope than buying a brand new one from a store with a return policy.
Yeah.
In particular, stores purchased from department stores, for some reason, the truth in advertising laws are not enforced.
Right.
No.
Has had telescope clinics where we invited people new to astronomy to bring their telescopes in so that we could set them up and test them and align them for them. And we found a large number of people never got their telescope to work, in some cases because the stuff was broken or badly designed.
Mm-hmm.
So my suggestion is if you're thinking of your first timer and you're thinking of getting a used scope, get the advice of somebody more experienced.
Yeah, that's big. I always keep suggesting borrow equipment, rent equipment, go see somebody else's equipment. That's one of the nice things, at least with amateur astronomy, is you normally, at least with a reasonable club, have an opportunity to try out other people's stuff. And you can decide, like it or not.
A lending library of telescopes.
Yep. So there's plenty of opportunities, but put off the purchase for as long as you can. Because part of it with a telescope, and this is something a lot of people tend to forget, is there are a lot of personal preferences involved. How comfortable are you? How much nuisance is it to set up? And these are all very personal things. Eyepieces, for example. I have terrible eyesight, and eyepieces that I absolutely love, a good friend of mine absolutely hates. But for my terrible eyesight, they work fine. So you really got to look at the personal things. So the more you can try out before you buy anything, the better off you're going to be.
And frankly, go to a local store. And we are blessed in Ottawa. We have a local store.
And
they provide excellent service. I still remember all those years ago when I went in and said, I'm looking for a telescope, and I didn't know what the hell I was talking about. And they said, well, why don't you take this one home, leave a deposit, have a look through it, and then come back and tell us whether it fits what you want to do.
I know
in fact,
it
the
sounds
first
like
question they asked me was, what do you want to do?
I know it sounds like we're shilling for them, but I mean, they do a good job.
It's not a matter of shilling for them. It's a matter of letting people know that there is a store out there. All they have to do is Google telescopes Ottawa, and they will find it for themselves.
Yep.
I think that's definitely very good advice. And I would, and also that I've seen sometimes people occasionally be very frustrated with their equipment. They say their telescope, they think it's a piece of junk. It's not giving sharp images. And then when I looked into it, I realized the optics were completely misaligned. So the mirrors were off. And I said, well, this needs to be adjusted. And once it's adjusted, it will probably be an excellent piece of equipment. And they did it. And sure enough, they couldn't believe it. They thought it was a completely different telescope. So
yes,
having an understanding of the equipment and how it works really, really can help.
Yeah, it's no different to your car being completely out of adjustment.
Yes. I think part of it too, though, is you do have to manage expectations. And this is another advantage that you get of looking through other people's telescopes. You know, you're not going to see the beautiful picture you get on the cover of the magazine. It's not going to happen. I'm not even being cynical about this. Your eyes won't do it.
Yeah.
But there is something to appreciate with what you do see through a telescope, and it takes time to acquire that taste. So again, it's look through other people's stuff as much as you can before you decide.
Okay, Cicely has an extremely important point here. Plug RASC membership. Folks, come to our meetings. We will tell you, answer all of your questions. Well, under normal circumstances, we'll do it in person, but right now we'll do it virtually.
Yep, and you know, as Attila had pointed out, I mean, we're all amateurs. I mean, there are a few of us that are professionals. Most of us have other day jobs, or we're retired, or we do other things. So we can't guarantee that we can answer every question you have, but we'll certainly try. And try to find somebody who can give you a good answer. And there's a heck of a lot of things that we can answer.
Tim, even the professionals can't answer all of those questions.
The big difference is the professionals will never admit it.
Some of them do.
I know.
The really good ones do.
The really good ones will admit it. Sure. Yes. You know, like this geologist guy that talks at the RASC. You know.
I know. I know something about him, I think.
Seriously, though, I mean, the more you can get other people to help you out, the more fun you're going to have, and the better experience you'll have, because you'll have gear that suits you.
You might be amused by this story. I've been giving basically exactly advice that Tim has taken for years to people, and as far as I know, nobody's ever taken it. Case in point, a friend of mine last year got into astronomy for the first time, and he promptly ignored all my advice and immediately went out and bought a telescope.
Yep.
Smart enough to buy it from a place that permitted returns. In short order, he went through 3 telescopes and wound up spending about twice as much as he originally intended, but he wound up with something that worked for him. He needed to go through a process of trial and error because he had basically no one to ask for advice, or he was impervious to advice. So basically the message is, don't assume that you'll get something you like without either trying telescopes more than once or being able to return them.
Well, if you go to your meeting, you're going to have a lot of people there who already have equipment that you can check out. I'm sure they'll let you take a look through it.
Actually, it's the telescope is the one you have with you. I disagree. The best telescope is the one your friend brought, paid for, and already set up, and wound up to look at for you, and then pack the whole thing up and takes it home. That is definitely the best telescope.
Yes.
It's the guy's telescope.
Well, unless you're a gearhead and you just love the fiddling. And there are people who are that. I mean, they just love playing with the toys.
We definitely need to restart the CARP star parties.
Yes. Well, there is a little virus problem here.
All right, it's 5:33, gentlemen. I believe it's time for us to have a supper break. Thank you all for contributing to our question and answer portion. So we are going to take a 30-minute break, and we will see everyone back at 6 p.m. starting with another introduction to astronomy talk by Dave Chisholm, this time aimed at a slightly older audience. Followed by Boyan talking to us about his passion, the use of night vision goggles to look at the night sky. Then Paul Cloninger is going to talk to us about his portable astro imaging control room for when he's out on the road or out in the middle of the Arctic winter doing his imaging. Andrea will come in at 8 to talk about her adventures beginning into astrophotography with a simple tracking setup. And then I will talk to you at 8:30 about how to be an urban astronomer. And at 9 p.m. we will start the final section of our event, which will be a live star party. We'll see if the clouds part enough to get some live images from the night sky. If not, then our members have lots of pre-recorded images to share with you to give you an idea of what it is that we like to look at in the night sky. So thank you everyone for the afternoon session, and we will see you at